Hello? Okay. Yeah, 10 more minutes. Yeah, blackboard. Yeah. Yeah. Okay. Okay.
Good morning. Welcome, everyone. Shunsei will continue his final lecture on multipartite entanglement in many-body systems above one dimension. Yeah.
Thank you. Good morning, everyone. I will continue on the multipartite entanglement, in particular the Markov gap. But last time I started description of topological phase, so I consider two-dimensional topological quantum field theory, and then I consider Markov gap there. The setup is as follows. So we consider some TQFT. It can be something like Chern-Simons theory. And then we consider some space. I think it's most convenient to consider maybe the two-dimensional sphere. So this is my space. And I'm not drawing a time, but I have a two-dimensional space. And then on this two-dimensional space, I have some wave function. So I have a ground state wave function, let's say. Ground state of topological quantum field theory. And then I start to partition this space. In particular, we can consider bipartitioning. So maybe I can consider splitting this sphere into two regions. Region A and region B. And then we can consider a entanglement entropy associated to region A. Okay? So this is a very famous, there's very famous result, which I will perhaps mention a bit more on that later. But the behavior of the entanglement entropy is well understood. It has a following form. So we have a the leading term, which depends on the size of region A, and then there is maybe some coefficient, which is non-universal, and then it's not. Maybe it's interesting, but it's not as interesting as the next term I'm going to write down. But anyway, the leading term is proportional to the size of A, maybe the circumference. Circumference, I'm writing it as LA, the size of the entangling boundary. So this is just an area term. And then, interestingly, there's the sub-leading term, which is called topological entanglement entropy, TEE. So this part turns out to be universal. I guess I mentioned this last time. As it turns out, this S topological, once again, it's universal, and then maybe I write this as minus S, I guess, or maybe I don't write this way. So as it turns out, it is related to the topological property of topological quantum field theory. So last time I mentioned anyons. So topological quantum theories support gapped excitations, particle-like localized excitations, and they obey interesting statistics. So they're called anyons. Typical TQFT support various kinds of anyons. So we can label type of anyons by using some label. Doesn't matter, but let's say I use label I to represent anyon. So I have a anyon of type 1, type 2, and so on and so forth. And each anyon has their own statistics, and then there are also mutual statistics as we exchange the position of different kinds of anyons. Usually, we reserve this 0 as a trivial anyon. We include a trivial particle. That is nothing but just a ground state of vacuum. But anyway, this is just a convention. So usually we have a list of anyons supported in a particular topological phase. And then this topological part of entanglement entropy captures the properties of anyon. So important properties of anyon. I mean, there's a set of data characterizing anyons. So, for example, I can describe properties of anyons by drawing their world lines. I consider some time, and then I can create anyon from, let's say, vacuum. Like we create pairwise create anyons of type A. Okay, and then I could also create another pair of anyons. Maybe I use I here and J, and then usually these carry their antipart. If I create an anyon of type I also create the antiparticle. So anti-anyons, I call it, let's say, I bar. And here similarly, I create J anyon, and then its antiparticle J bar anyon, and then they can propagate in time, right? And then eventually they can exchange their location. Maybe I draw some, I imagine some process like this I bar and this J anyons, they exchange their positions. And then eventually they may, pair annihilate again. I think this is the right diagram. So there's certain amplitude associated to this type of process. Usually this amplitude for this process, we call it Sij, or we call it S matrix. Yeah, maybe I can write it here. Okay. Yeah, maybe it's a bit too dark. Okay. And we have to switch, I guess. Okay, good. So let me continue on iPad. Okay. Right. So there are not just a single number to fully characterize a topological quantum field theory. There's a set of data, but this Sij is is one such a set of data. It looks like a matrix. So I and J both run for the set of available anyons. So this is called S matrix. Or more precisely, it may be called modular S matrix. And then topological entanglement entropy is it's a log of minus log of S00. Okay. So it captures topological entanglement entropy captures a part of topological data. This is also called quantum S00, or its inverse is sometimes written as D, and then it's called just quantum dimension. But these are just terminologies. Okay, so this is a famous result by Levin and Wen and Kitaev and Presko around 2005 again, I think. Yeah, 2005. So this has been very useful. For example, if you have a numerical simulation of some very complicated lattice spin model, and then if you are lucky, you may be able to realize interesting ground states such as topological spin liquid. And then one way to diagnose or detect topological spin liquid is to look at the scaling of entanglement entropy for subregion as a function of subregion size. And then you should see area law. If you don't see area law, you are getting something else in the first place. But if you are getting area law, you may be interested in interpolating this area law scaling, and then you can read off this intercept, which may be, first of all, if it is negative, there's a good chance that you are getting topological spin liquid. And the second of all, this number itself, it may tell us the type of spin liquid. We may get different topological spin liquids may be described by different topological quantum field series, and we may want to distinguish them. And this number may be good, maybe a good way to differentiate different possibilities. Okay, but unfortunately, since topological entanglement entropy is just part of data, not the full set of data, some topological states share the same topological entanglement entropy. For example, topological entanglement entropy can be log 2 for something called Z2 spin liquid, or it is also known as something like a toric chord or something like that. It's a canonical example of Z2 spin liquid, which may have been already realized in the quantum simulators, for example. But on the other hand, there's also something called Ising topological. Ising, what is a good terminology? I think, yeah, quantum field theorists may call it Ising TQFT. I think for condensed matter physicists, this is a maybe something we may call chiral p-wave superconductor. But anyway, there's some other topological phase which is even more interesting than Z2 spin liquid, which is this topological phase is famous for the Majorana fermion excitation. So many people are interested in realizing this Ising topological quantum field theory. But as it turns out, just from the point of view of a topological entanglement entropy, for both phases, topological entanglement entropy is just a log 2. So we cannot really distinguish these two possibilities. Okay? So that is a kind of part of the motivation to look into more finer characterization. And then, today I want to discuss the Markov gap. Just right? Yeah, okay, so just right. So we are then interested in maybe Markov gap, which is the reflected entropy minus mutual information. And then, yeah, as before, I consider a topological system put on a spatial sphere. And then previously, I bipartitioned the sphere into two regions, but this case I tripartition. So the picture is going to be slightly more complicated, but it may be looking like this. So now I have three regions, A, B, and C. And then I choose a geometry such that these three regions meet at a single point or 2 points, like a trijunction. Okay, so there are two special points in this partitioning. And then in principle, I could also just consider a plane. And then I can consider similar partitioning. I have a region A, B, C, and these subregions, they all meet at a single point on the plane. But anyway, either way, I consider some special manifold, and then I consider multi-partition, tripartition of these special regions, and then I can discuss reflected entropy, let's say by tracing out region C, and then also mutual information, and then the difference gives me the Markov gap. Okay, So this is the setup. Okay. I think it's simple enough. But if you have any questions, please stop me. So then I just want to introduce some recent result about this Markov gap for this setup. So H is actually given by this formula, C over 3 log 2. Okay, so yeah, it's a very simple formula. There's no dependence on the size of region ABC. So the size dependence cancel as we take this difference. So RAB, IAB, each, they depend on the size of region ABC. But if you take a difference, the size dependence goes away. But then we are left with a universal number. And what is the C? C is the central charge. And central charge, if you wish, it's another number, universal number, that characterizes a topological theory. But this topological number or topological invariant is associated to the boundary of topological field theory. So if you have some topological field theory, TFT, or topological quantum field theory, let's say in 3 dimensions, 2 plus 1 dimensions, but then you can make a boundary to the system. So let's say I make a boundary here. Yeah, I don't know what is the best way, but let's say I have a boundary here. So this is the 3-dimensional space-time is boundary, and the boundary is 2D. And then TQFTs are known to support boundary excitations, which is described by a conformal field theory. Okay, so this is the different from bulk excitations, such as the anyons. Anyons are bulk excitations, but on the other hand, on the boundary, we have a seemingly different kind of excitations, and they are described by conformal field theories, which are gapless degrees of freedom. So as it seems, there are 2 kinds of excitations. One of them, they are in the bulk, so anyons. On the other hand, on the boundaries, there are gapler excitations. They look just 2 kind of separate excitations, but as it turns out, they are very closely related. And then this close correspondence is known under the name of bulk boundary correspondence. It's a bit like ADS-CFT, but I think we should distinguish the bulk boundary correspondence in topological phase and the ADS-CFT, I guess. But anyway, this is the bulk boundary correspondence in the topological quantum field series. So one of the dictionary is a type of. So I described there are a label type of anyons. Let's say I use I to describe such a. I mean, I don't have to perhaps use 1, 2, and so on and so forth. But anyway, I need some label to describe anyons in the bulk. And then there's a correspondence between anyons in the bulk and then the excitations on the boundary, which are described by CFT. And then CFT, it comes with a set of operators. And in particular, there are important kind of operators. They're called primaries. Primary operators. And the primary operators, you can also label them and count. Okay? And then they comes with some conformal dimension HI. So at least one part of this bulk boundary dictionary is the correspondence between these anyons and the primary operators on the boundary. So they are 1-to-1. So that's the bulk boundary correspondence. Yes. Yeah. So you're absolutely right that I could choose different boundary conditions. Um, um, so yeah, it may actually play an important role here. Here, I'm mostly describing chiral topological series, and for the chiral topological series, the possible boundary conditions are kind of very limited, and then you get just a gapless conformal Fourier series. I think you are forced to have a gapless conformal Fourier series. There are other kinds of topological Fourier series. For example, I mentioned Z2 spin liquid. Z2 spin liquid allows at least two kinds of boundary conditions, electric and magnetic boundary conditions. So you can clearly choose some boundary conditions there. So yeah, actually there's more life, but this is kind of simple one. Yes, yeah. There's also kind of correspondence between the type of boundary condition, type of gapped boundary condition you put there, and the data in the bulk data. So if you know the bulk data, you could guess what kind of a gapped boundaries you could get. Here it's a gapless one, so that's why I'm saying it's a simple one. And then yeah, I think I already mentioned something about that a bit more. But here, let's say this is a simple version, which we have a chiral theory. Okay. Right. So the central charge here, sitting here, is the central charge of this boundary theory. Central charge of this boundary or edge series. I think boundary CFT is a bit confusing terminology, so I call it edge theory. Okay. So this is the first result. Yeah. So that's the I think for many of us physicists, that's sounds like a very unmotivated name, unfortunately. But this the Markov gap is the name invented by quantum information slash physicist. So there are people who are more kind of inclined to quantum information theory way of thinking about this. So this gap here has nothing to do with spectral gap. But this entanglement quantity has some meaning in terms of the recovery channel, which unfortunately I can't really explain now. But this gap is somehow related to the ability or inability to recover this recovery channel. So it has nothing to do with spectral gap, I should say. A question? Yes. Yeah. Details. Yeah. Yeah. Yeah, there are a lot of details I should tell in principle. So for example, I just described one topological data, actually here on the blackboard, this S matrix. And then there's many data describing the anyons. For example, this is the data more or less associated to the braiding of anyons. But anyon can also fuse. They can combine to create different excitation. That's called a fusion of anyons. Or they can also split into different kinds of anyons. So these are their set of bulk data. They are more or less described by set of diagrams of this kind. So you draw kind of Feynman diagrams, and each Feynman diagram comes with some number, and then some relations or constraint among such numbers. So that's a bulk data. We have a similar data in conformal field series, which actually we are going to make use of. So primary field, they are like, oh yeah, maybe I should. So the primaries, so we have a primary operators, let's say OI primaries. And then they also have modular S matrix. For example, if you consider a partition function this may not be the best way of saying this, but for example, if you consider partition function of conformal field theory, where H is 2 pi over L, naught minus C over 24. And then you can consider partition function for given tower of state associated to given primaries. Let's call it chi I. And then Q is 2 pi over L times, sorry, this is 2 pi over L. Temperature divided by, beta over L, yeah. Anyway, there's some number here. Usually we use Q here. And then modular S matrix in conformal field theory can be defined in terms of this partition function associated to a given primary. So, oops. So I have a two-dimensional space-time. This is space. And then there's a periodic boundary condition. And then the length is L. And then I also have a time direction, which is also periodic. And then I use beta, inverse temperature. So I have a partition function associated to this geometry. But you can also consider a partition function, slightly different partition function. I use J in the space-time geometry where the role of space and time are exchanged. So I use different symbol Q tilde, and then I use H. Hamiltonian looks the same because of Lorentz invariance. So time translation in X and time translation in T, they look the same. So Hamiltonian looks the same because of the Lorentz invariance. But since I exchange the role of beta and L, Q tilde here is exponential of inverse of beta over L because I exchange. So I'm not sure about actually the coefficient here, but let me put 2 pi here. Okay, so this is chi J Q tilde. Okay, this is chi I Q. And then S matrix in conformal field theory is a relation between chi in the original frame where this direction is space and this direction is time. But we can also relate this to the partition function in the other frame. But there's a linear relation. So that's how S matrix appear in conformal field theory, and we are actually going to make use of this fact to compute topological entanglement entropy. And then I think other way to say this is that other data are also related to primaries. If you have a correlation function of primary operators on the plane, let's say, maybe I consider 4-point. So this is a complex plane. This is a complex plane. And then you have some correlation function, or I, or J, or K, or L. And then you can think about adiabatically moving the location of these operators. And then this correlation function pick up some monodromy. That's also kind of very similar, or by this dictionary, it's basically equivalent to the braiding of anyons in the Barg language. So there's such a very interesting correspondence. I'm just use this fact in the later calculation. Okay. Yeah. Okay. Other questions? Okay. So hopefully, I mean, like I said, there's more. Perhaps entire lecture or entire week can be devoted to just describing bulk edge correspondence and TQFT. But here today, I'm more interested in just entanglement properties. So yeah. Yes. Yeah. Yeah, so you can think about I draw word lines, but word lines we can think about Wilson line, insertion of Wilson line operators. And so, yeah, I didn't perhaps use the this language like line operators and so on and so forth, but that's basically the same thing. And then the bulk boundary correspondence, maybe I should say, maybe another way to state is that I can draw bulk Wilson lines, but if I have a boundary, Wilson lines can end on the boundary. So that's how we make a dictionary or correspondence between bulk and boundaries. Yeah. Yeah, usually Wilson loop, for example, it may have an interesting relation to the 2/5 loop, but Wilson loop alone, they don't have interesting statistic among themselves. But I think here it's a it's a Chern-Simons term which describe the self-linking properties. So there's some interesting parity breaking term which is playing a role. For example, if you consider Z2 spin liquid, there's no interesting statistics just for the charged Wilson loops, but there's interesting statistics between charged and electric and magnetic groups have interesting statistics and so on and so forth. And you also said fermions and bosons. Yeah. Yeah. I mean, the regular one doesn't have, for example, Fermi statistics. Yeah. Yeah. Okay. Other questions? Yes. Yeah, so partition function is the partition function I introduced is the partition function of edge theory, not the bulk theory. So anyons are bulk excitations. By the dictionary, it is related to the primaries in the edge series, and for each primaries, we can define partition function of conformal field series. Okay, I hope it answers the questions. Yes. Uh-huh. Is it what? Fractional quantum Fourier. Yeah. So this is the yeah. So I just said fractional Chern-Simons theory because it's maybe more familiar to this audience. Yeah, questions. Yeah. But yeah, example is the Chern-Simons theory. Or yeah, fractional quantum Hall effect. So for example, I can just consider U1 Chern-Simons theory. The action looks like this: K over 4 pi A dA. Okay, and then in terms of fractional quantum Hall effect, this is the, I'm not sure to this audience it makes sense, but you can consider fractional quantum Hall effect at the filling fraction, which is the ratio between number of particles and the magnetic flux in the system, and then you can consider fractional filling fraction 1 over k. The same k here is the coefficient of the Chern-Simons term, but it has a realization as a fractional quantum Hall effect at filling fraction 1 over k. And then the bulk excitations is anyons, but I perhaps write the Wilson loops, which is E2 I some number, let me put m here. So this is the you can write the set of different kinds of Wilson loops with different coefficient where m goes from 0 to k minus 1. Okay, but in terms of fractional quantum Hall effect, these are different kinds of ruffling quasi-particles. And then they carry fractional charge. Fractional charge, which is m divided by k. And then you can also get a edge theory. Which is the one of the simplest conformal field theory, which is the compactified boson. So I can write the action for the compactified boson with some more terms possibly, but it may be looking like this. Maybe 2 pi. Yeah, sorry. This coefficient I'm not sure, but it's something like k over pi or 2 pi. So the boundary theory is just a free scalar theory, and then you can write down. Yeah, so I just maybe continue here. So within edge theory, you can write down a primary operators. These are given by exponential I times. Yeah, sometimes the normalization is a bit annoying, but let me normalize this way, and then I can also put m here. So this is the operator within conformal field theory, edge series. Okay, so but you can see that this set of Wilson loops or Wilson lines in the bulk, there's some nice correspondence with the primary operators in this free boson conformal field theory. Okay, so this is the kind of correspondence I have in mind. Okay, I hope this somehow answers the question. Okay. Other questions? Okay. Right. So let me now mention a few more words about this result we got. So this is a first of all, this is a new way to extract new topological. I mean, the topological data which are not captured by topological entanglement entropy. It seems like we can capture it, the central charge, by using this Markov gap. Okay, so it may be in principle as useful as topological entanglement entropy. So now we can distinguish perhaps more phases by looking at both topological entanglement entropy and Markov gap. And then the maybe second thing I want to mention is that this is the result at topological quantum field theory. And then topological quantum field theory, we can think of this as a renormalization group fixed point. But you can think about perturbing topological quantum field theory. So if I consider phase diagram, maybe there's some parameters, I don't know. So there's a G1, G2, and so on and so forth. If you have some microscopic Hamiltonian, so there's some region in this parameter space, we may have a certain topological phase. And then the outside, we don't know, it may be some other phase, maybe gapless phase, or maybe some other topological phase, or it can be trivial phase, and so on, so forth. So there are other phase 1, there are other, I don't know, phase 2, and so on and so forth. Okay, but this result is the result within topological quantum field theory, and the topological quantum field theory is the RG fixed point, just like conformal field theory is the RG fixed point. So it is like one point in this phase diagram where RG flow takes you, if you start from somewhere in this in the topological phase, RG flow takes you to this fixed point. And then at this fixed point, we computed this topological this Markov gap is given by this universal number C over 3 log 2. But one may be also interested in what what is this Markov gap around the RG flow? Okay, I guess if you start from somewhere here, it's a different phase, so we cannot really use anything. It has nothing to do with the given topological quantum field series. But let's say if you are starting somewhere here, it's not exactly a topological quantum field theory. It's a topological quantum field theory with some irrelevant deformations. But you can ask what is the Markov gap if you are not exactly at this critical at the fixed point. So there's no analytical calculation we can do on that. I mean, we may, but right now there's no analytical result available. But numerics suggests that h, if we are not at the fixed point, h is not c over 3 log 2 exactly, but as it seems, h is bounded from below by c over log 2. Okay, so if you are not at the fixed point, you may see Markov gap, which is bigger than this result. And then as you flow into this fixed point, the h decreases, and eventually we get c over 3 log 2. But generically, within this phase, h seems to be bounded from below. Okay, this is like a numerical observation. We don't have any proof for this, but this is the looking at some examples. This is the behavior we saw. Okay. Yes. No. So this is the So topological. So this point is a topological quantum theory. Just Chern-Simons theory. But you can think about adding some perturbations, for example, Maxwell terms and so on and so forth. So Maxwell's term in 2 dimensions has more, irrelevant because ADA has one less derivative, so it's more relevant. So you can think about deforming Chern-Simons theory by adding irrelevant perturbation. And then if you let RG flow run, eventually a Maxwell term goes away, and then you end up at this fixed point. Yes, so that's right. This is the microscopic picture, but yeah. Maybe I should draw single line, which is simpler. But microscopically, we have more parameters. Yeah. So it's a theory space diagram. Yeah. Okay. So microscopic Hamiltonian can have different phases. Right. Yeah. So that may be a bit of a terminology question, but yeah. So microscopically, clearly we can change a lot of parameters in the Hamiltonian. So for example, you have a fractional quantum Hall effect Hamiltonian. You can change filling fraction, but you can also change the form of microscopic 4 fermion interactions, the mass, and so on and so forth. So there are many parameters. And then we of course, microscopic Hamiltonian is not exactly like a Chern-Simons theory, but low energy effective field theory is Chern-Simons theory to the leading order. But then there's some irrelevant deformation of Chern-Simons theories. These are not important to describe topological properties. But nevertheless, if you wish, we can think that it's always there. It's always there. Okay. There. I hope it's clear enough. The other questions? Okay. Yeah. So let me go on. So So this is the. I guess we don't know much about this quantity yet, but these are two things we know. So now there's a foreign conjecture. So this is not our conjecture, but this is a conjecture by UC Berkeley group, Siba, Zhou. Sorry, there's no H. Zhou. Suejima. Mon, Zaratel. It's the same group who studied 1D Markov gap, but they also studied 2D case. So they put the following conjecture. So in general, if you are in the topological phase, so if you are somewhere in the topological phase, you can ask what is the Markov gap, and then the way they phrase this, their conjecture is that Markov gap is given by C over 3 log 2 if you optimize your state. So you have a ground state of your microscopic Hamiltonian, and then as I mentioned, if you just compute a Markov gap on a given ground state somewhere in this phase diagram, it's bigger than C over 3 log 2. But you can think about applying some, you allow yourself to apply some local unitary operator on the ground states so that you can tune this unitary operator to try to reduce the Markov gap as much as possible. But the claim is that no matter how you change your U, you cannot really go lower than C over log 2. And that is the first part of the conjecture, which is already, kind of already mentioned this in slightly different language. But the another part of the conjecture is that this central charge here is the central charge for the ungappable degrees of freedom. So that's related to our discussion before, where we can choose different boundary conditions. So depending on the boundary condition you choose, sometimes we may be able to, in the simplest case I just discussed, there's always some, in the simplest case I discussed, I didn't mention much about the choice of the boundary physics. In the previous dictionary, I kind of pretending there's only one, but in principle, you can gap a part of the boundary degrees of freedom, but it so happens that sometimes you cannot gap all degrees of freedom. You can perhaps partially gap your edge degrees of freedom, but some gapless degrees of freedom may still be left. Okay, so that's the ungappable degrees of freedom, and you can characterize the total ungappable degrees of freedom by looking at the central charge. So their conjecture is that the central charge sitting here is the central charge of the ungappable degrees of freedom. Okay, maybe this is maybe a bit too detailed, but I think this is a very interesting conjecture. Okay, so once again, there's no proof as far as I know, but there's many examples we looked at, and then this type of behavior seems to be very, very reasonable. Okay, so this is the current situation, and then maybe I pause here and if I ask if there's any questions. Okay, so so this is something you can just choose. You get your ground state, but the idea is that if you are not exactly at a fixed point, your ground state is not exactly the ground state of topological quantum field theory. It's maybe slightly deformed, and then you can deform your state nicely if you move inside the phase diagram. But the way they're phrasing is that instead of changing the locus in the phase diagram, you just brute force modify your state by applying some unitary operators. And then if you choose your unitary operator in the right way, you may be able to reduce the Markov gap, and you can kind of try very hard to minimize your Markov gap as much as you can by applying some local unitaries. But the conjecture is that there's some limit for this. You cannot go below C over 3 log 2. Okay. Yes? Sorry, I didn't get the which calculation? Minimization, yes. Is related to, sorry? Yeah, that's the idea. So you are adding some. You are trying to modify your state by adding, I don't know, adding irrelevant perturbation, and then if you choose the direction in the right way, you can reduce h. Okay, but there's some limit. Yes, I mean, yeah, I guess this way of phrasing is maybe more conventional. I mean, more familiar to condensed matter physicists, and I realize this may not be the way usually maybe phrased in the quantum field theory language, but it should be basically the same meaning as this. And then, but other important part of the conjecture is that this meaning of this center charge appearing here. Okay. Okay. Other questions? Yes. Yeah. So this is so far. I mentioned a boundary theory, but calculation, this entanglement quantities like H and the reflected entropy and the mutual information, we basically compute all these quantities without the boundaries. Just I want to make sure. So for the calculation of these, there is no physical boundary. I just consider bulk topological system. But the claim is that these quantity seems to capture something related to boundaries. So there's no physical gap, physical boundary. But somewhat interestingly, these quantities captures a boundary physics. Yeah. Another question. That's the. Yeah, so it may be related. I think in the optimization of the entanglement purification, you may also have to optimize over purifying partner, and then here it's not clear if there's such thing there, but it may be related. Yeah. So yeah, one may wonder, is there something similar for actually just entanglement purification, but it's much more difficult to compute, unfortunately. Okay. Other questions? Okay, so if there's no question, or you can ask me later. I just want to say a few words about the actual calculations. So the idea of calculation actually make use of bulk boundary correspondence. So we have a 2D bulk, a spatial bulk, and I make an entangling cut. Let's say let me just do this calculation for just entanglement entropy, and then I just generalize this calculation to the reflected entropy. But let me first consider just entanglement entropy calculation. So this can be computed in many ways. Entanglement entropy can be computed in many different ways, but I want to choose to use the bulk boundary correspondence because that's this type of calculation can be generalized to reflected entropy. So the idea is that we need to know the ground state of this topological phase, or we are given a ground state on S2. Now, but we are bipartitioning this sphere, and then to get entanglement properties, it is sufficient to know the ground state near the entangling boundary, only near here. Because this is a fully gapped system, I mean, if I'm at the fixed point, gap is in some sense infinitely large. So that means there's not really, correlation functions all decay exponentially fast or almost zero in the topological limit. So when we are computing entanglement entropy, the contribution to the entanglement entropy come only from the very close region very close to this entangling cut. Okay, so we focus on, we can in some sense forget about the regions very far from the entanglement boundary. So we focus on this region. And then the idea, I brought the idea by a Chi Katsura Ludwig, where they found out that the ground state near the entanglement boundary or entangling cut is given by the boundary state in conformal field theory. Okay. So what is a boundary state? So I first consider once again edge theory, which does not exist physically, but I imagine I have a virtual fictitious boundary at the entanglement boundary. And then once I have a boundary, there's the unconformal field theory degrees of freedom. Okay? And then there's the two boundaries, boundary of region A, and then boundary of region B, and then they come with opposite chiralities. Okay? So I have a CFT A, maybe I do this, which describes the boundary of region A, and I have a CFT B, which describes the boundary of region B. And then we may want to use the degrees of freedom in these two CFTs to represent the ground state near the entangling surface. Okay. So once again, the answer is given by this boundary state, and then boundary state is a state which satisfies this condition: stress energy tensor on A minus stress energy tensor for V. So these are two CFTs. I have two CFTs. So I have a stress energy tensor for each CFT, and then basically TA is equal to TB within this state. So I may also write the coordinate here, but that's not very important. So coordinate is this coordinate which is periodic along the entangling boundary. So this is the condition for the boundary state. It may also satisfy more conditions. Okay. TA sigma, TB sigma. Conformal field theory may come with a certain current. For example, if you have a U1 Chern-Simons theory, there's a U1 current. If you have a SUN Chern-Simons theory, you have a SUN West-Zubin-Witten theory on the boundary, and then there's SUN current. So there's a similar condition for current in the CFT A. And then if you compare it with current in CFT B, they may be zero if you evaluate it. If you evaluate this difference for this boundary state, and then this is, if you wish, these are the defining relation of a boundary state, and then you can think about solving this constraint to write down the explicit form for the boundary state. Okay. So yeah, I don't do it now, but it's just you can write it down. So this is a particular form of this boundary condition with this current condition. It's called Ishibashi state. So we are going to use Ishibashi boundary state. Okay. So anyway, important claim is that Ishibashi boundary state, it's a state in conformal field theory, but idea is that it may mimic the 2+1 dimensional ground state as far as you are focusing near the entangling boundary here. Okay, so we make use of this idea. So what is the explicit form of this boundary state? It can be written in this form. So a state in CFTA, it is labeled by a primary that specifies particular type of state. And then for a given tower of states, starting from the lowest primary, you can basically build entire spectrum within this tower of state. And then there's some labels. For example, something called level. And then each level, there's a degeneracy. But it's not so important what these labels means, but we need some label to distinguish states in the different, within a given tower of state. And then we can pair up these states in CFTA with states in CFTB, and then we just consider a identical state. I put the bar here because CFTA and CFTB come with opposite chiralities. But basically, we CFT and the CFTB are, except for chirality, they are identical CFT. So we can make a pairing between these states. So I sum over n and k. So this is the specific solution to these boundary conditions. And then the once again claim is this, but I didn't write equality here. And then to make this connection between boundary state and the 2D ground state precise, I also put the regularization factor, which is given by the exponential of edge Hamiltonian, HB. It's such that you are summing infinitely many states, and we just penalize the very high energy state so that this sum somehow converges. So up to, the claim is that up to some normalization factor here, boundary state with this regularization factor is the faithful ground state representation. Okay, and once we know ground state representation, from here we can write down density matrix up to some normalization. It's simply given by this. But written this way, everything is explicitly written, so we can just trace out region B now, brute force. Okay, and then from the explicit expression of rho A, we can write down, we can basically compute entanglement entropy. Okay, so this is the simple exercise in conformal field theory. So for example, yeah. Summing. Yeah, so we are actually not summing over primaries. We are summing state within the tower. That's right. That's right. Yes. Regulating some. Yes. Yeah. You can just exponentially suppress the high energy state. Yes. Yeah. So yeah, I should have said that. Yeah. Thank you for that. And then, yeah, maybe I just do some calculation. So if you do this calculation, rho A up to some normalization turns out to be it's just h of A times 4, I think, times 4 epsilon, as it turns out. So then, if we are interested in entanglement entropy, we are interested in the moment of reduced density matrix, which is given by this form, chi I to power qn, where chi is the partition function I introduced earlier, and then q is something like this. Oh, sorry, there's no pi here. 4 times beta here. And then n is also related to this partition function, but we have to raise this to power n. Okay, and then we are interested in the limit where regularization parameter. Sorry, I write it as epsilon. Regularization parameter epsilon goes to 0, or epsilon over L goes to 0, and then this is conveniently computed if we first rewrite chi by using modular S matrix. Yes, so yeah, so maybe I didn't put I here, sorry. That's a good question. So I choose a particular tower of step, I choose a particular primary, and I choose a particular tower of state, Verma module. So yeah, maybe sorry, I didn't write I, but it comes with index I. Yeah, I choose a particular, particular lowest energy state. Yeah, so that's why it depends on I. Yeah, sorry, I didn't say that. Yeah, so that's right. So in the simplest case, we can just choose I to be 0. Yeah, but here it's sorry. I think I presented it a bit general way, because for example, we can also put Wilson line penetrating this entangling boundary. But yeah, here in the simplest case, I is just 0, in fact. And then we can write the moment of radius density matrix in this form. But to take this limit, we can use this S modular S matrix we introduced. And then with this limit, we can show that only j equal to 0 terms survive. Okay? And then this calculation extract, oh sorry, this is S. Okay. This is S. So then this calculation basically extract Si0 power 1 minus n. There's some contribution coming from chi, which we can compute, but let me just focus on the contribution coming from this S matrices. So we basically extract Si0 power 1 minus n. And then by taking the replica limit, so I have to multiply 1 minus n. And then we take the replica limit where n goes to 1. We get the log of Si0. And then if I is 0, which is the simplest case, then we get the log of S00. And then if you remember the topological entanglement entropy formula, yeah, sorry, this is on the blackboard, I guess. Yeah, topological entanglement entropy is given in terms of a log of modular S matrix Si0 or S00. Okay, so that's how we derive a topological entanglement entropy. And in the conformal field theory context, this quantity is known as boundary entropy. And then this is kind of different interpretation. In conformal field theory, it is a boundary entropy, but in terms of a 2 plus 1D TQFT, boundary entropy is a topological entanglement entropy. Okay, so I think I had to somehow cut some details, unfortunately, but if you want to know more about this calculation, you can ask me later. Are there other questions? Okay, so this is the calculation for bipartition. But now we want to do something similar for multi-partitioning. So we do something like this. Okay. And then, but the idea is very similar. Since it's a fully gapped state with very short range correlation functions, we maybe just focus on the degrees of freedom near the entangling boundaries. And then we may want to find a state within conformal field theory. But now we have a 3 conformal field theories because I have a 3 regions A, B, C. And each region has its own boundary here for region A, here for region B, and here for region C. So we have a 3 CFTs involved, CFT A, B, C, one for each bulk regions. And then we may want to find such state where B, I write it as B, it's something analogous to boundary state, but we are now interested in finding a state which satisfies this condition, where I is A, B, C, and then we may have a similar condition for the current. Oh, sorry. It is important that I have to put 2 pi minus sigma here. So once again, we are interested in finding some state in a product of conformal field series, in this case, product of 3 conformal field series. And then you can write down the condition which represents this connectivity. This is analogous to the boundary state definition of the boundary state we had for the case of bipartitioning. But I have to put 2 pi minus sigma here because part of A interact with part of B, but the other part of region A interact with a part of region C. Okay, so sigma is from 0 to 2 pi as you go around this entangling boundary. But in this condition, sigma runs only from 0 to pi. Anyway, that's something you can convince yourself that this is a proper condition. And then you can look for a solution to this state V. And then this is unfortunately a bit complicated calculations. For the bipartition, I knew the solution was the Ishibashi boundary state, so that was already recorded in the literature. As it turns out, this type of state was also discussed in the literature in the context of string field theory. But somewhat surprisingly, string field theory has application here for the physics of topological quantum field theory. But this solution was discussed, but only for free theories, like free fermion theories and free boson theories. But anyway, free boson theories or free fermion theories, they are already useful because, for example, for the Chern-Simons theory, edge theory is a free boson theory. So anyway, for some examples, we can construct the solution to this constraint equation. And once we get this state B, we basically follow the same procedure as we did here. We construct a density matrix, trace out some region, and then we can go ahead and compute entanglement quantity. So this is something we did first for free fermion and free boson theory. But unfortunately, I don't have calculation is a bit complicated, so unfortunately, I don't have a time to describe it today. But this strategy works very well for free theories.
One question from chat.
Yes.
Where is the state we defined on the junction of boundaries?
So the bulk state is defined for this S2. Okay, but then entangling boundary is these. Yeah, sorry, my drawing is not particularly good here, but there's the entangling boundaries here, and then there's a junction in the entangling boundaries. Okay. But we now consider a conformal field theory near the entangling boundaries. So, for example, for region A, this is my entangling boundary, and for the region C, I have a similar boundary. Oops. Okay, so I don't mean to erase, but Yeah, so there's a similar boundary for region B. So we have a three edge state, which are all located near the entangling boundary. Sigma is a coordinate along this one-dimensional spatial boundary. Yeah. Yes. Yes, exactly. So let me draw this picture again. So for simplicity, I just forget about periodic boundary condition for now, and the sigma starts from, let's say, from here 0, and then maybe end it here 2 pi. So this is the boundary of region A. Okay, so I have a coordinate here, and for region B, I have a coordinate sig for the boundary of region B, which starts from 0 and increase, and then it ends here with 2 pi. Okay, and similarly for C, I have another coordinate sigma, and then by looking at this picture, part of region A, let's say sigma 0. In this segment of edge theory for A, interact with the edge theory for region C for this region. Yeah, so sigma is restricted to this region, but this is interacting with a sigma between 2 pi and pi for, yeah. So this is clearly this is a very complicated expression which I didn't explain before. But anyway, this is the idea. Okay, so we write down the sort of boundary condition representing this geometry. Okay. Okay. So I think I will have like 3 minutes left, I guess. So anyway, so this calculation can be done, but so far only for free series. In the forthcoming paper, we are extending the calculation to generic conformal field series. Then I can perhaps just quickly tell you the idea. Well, maybe it's too much. I'm not sure. Anyway, yeah, maybe it's too much. So I perhaps just say this can be done. Construction of this state can be done for free series, and it was done. But right now we are working on to generalize this calculation to generic conformal field theory or generic edge series, and therefore generic topological quantum field theory, which does not involve the explicit construction of V, but we can avoid that construction so that we can do the calculation for generic conformal field series. And then the result is that we just confirm this result. But now we can basically do this calculation for generic case. Okay, since I'm running out of time, I think if you want to know more about this, you can come talk to me. Just for closing, I think I planned it to present also something about the dynamical process, like how Markov gap changes as a function of time if you consider something like a quantum quench. We did some calculation there. So once again, I'll be here today and also tomorrow. So if you want to know more about this, you can come talk to me about time dependence of Markov gap in quantum quench in conformal field series. Okay, anyway, so I think the overall theme is that we are interested in the finer entanglement structure that are just detected by bipartite entanglement. Okay, so that's entanglement entropy has been useful, but sometimes we want to know more about quantum states and the quantum entanglement in interesting states in many-body physics. And then Markov gap may be one such quantity. And there may be more, but so far we are working on we work a little bit on this Markov gap. Okay, thank you very much.
Yeah, questions?
I just like to ask about a little bit of details. So it seems that you are just imposing energy momentum tensor and the current continuity across the boundary, right?
Yes.
And why it gives non-trivial information about this, the entanglement topological
Yeah. So yeah, I think in some sense, maybe from that perspective, even for the case of bipartitioning, one may wonder why do we get topological entanglement entropy from this type of analysis? You just impose conditions, current on A, current B just match, and we just solve this constraint. Yeah, I can't say something very intuitive, but yeah, in some sense, in this case, the physics of boundary entropy, and then topological entanglement entropy. As it turns out, this seems to be very closely related. So that was the case, and then similar intuition may exist for the tri-party case, but it's much more involved because we know much less about this case. Yeah.
And just a similar question also in the one transparency before, you did a modular transformation.
Yeah.
And why one frame is easier than the other? So
yes.
can you just
So
point
that's
out?
part I think I also kind of skipped around, but we are interested in this limit. So if you wish, in the regular terminology, this is a high temperature limit. If you think of epsilon as an inverse temperature, so epsilon goes to zero. Usually, kind of more trivial or simpler limit is that where epsilon goes to infinite, which is a zero temperature limit. In that case, we only pick up ground state contribution. But if you go to high temperature, we have to sum almost all state with almost all equal probability. But this modular S transformation have the ability to exchange a space and time, and therefore epsilon and L. And now we can just consider limit where L over epsilon is large, and then in the once you exchange the space and time, L is basically like an inverse temperature. So in the rotated new frame, this is a low temperature limit where we can make calculation easily. Okay, yeah, clearly I didn't explain this part once again, sorry. Yeah.
So similar to this case, this what is it, Markov gap? Can you introduce a primary field or Wilson line and then generalize
yes,
it?
yeah, that's right. Yeah, so that's we did something like this for free fermion theory, and then we can sort of thread some flux, and then it may be interpreted as anyons. And then, it's not C over 3 log 2. We get something else. But the first result we got is, at the last step, we had to do some numerics. So we don't have any, other than we get something, different from C over 3 log 2. We don't have much intuitions for that yet.
So you don't have modular transformation for that.
Yeah. So in the forthcoming paper, as I advertised, we are doing it in a more general way and hoping to get some more analytical control and analytical understanding by putting anyon or Wilson lines, Wilson loops. But then in the end, the calculation without Wilson loop, we managed to complete almost. But the calculations with Wilson loop are a bit more complicated. So currently we don't have any understanding for that. But that's a very good thing to do. Yeah.
More questions? I have a very naive question. Is there a way to calculate, the former simple topological entanglement entropy and this Markov gap based on bulk topological field theory directly?
That's right. That's a great question. So I proceeded in this way because for the calculation of Markov gap, I think we couldn't find any other way. But for the entanglement entropy, we can just use bulk topological quantum field theory. I think somebody asked this question last time. And then essentially you can reduce the calculation to TQFT partition function calculation or something called state sum calculation. And then in the end, topological entanglement entropy is related to the partition function of TQFT on S3.
Reverse replica trick.
Yes. You just write down the 2 + 1 the path integral, do replica trick, and then you can eventually get this result. But we couldn't find such a calculation for Markov gap. We don't know how to do it.
One day you showed.
Yes.
I see.
Yeah. So that was CFTs. That was possible. Yeah. So yeah, that's right. So I think here's the first of all, if it works that way, that is very interesting. But we don't know. I think another question is in the simplest TQFT partition functions, they usually only capture central charge mod 8. But here we get some result which depends on central charge itself. So usually bulk TQFT data doesn't know about the absolute number of central charge. It's only know the central charge mod 8. So I'm not even sure if just a simple TQFT calculation can extract this number. The maybe a tricky point is that there's this trijunction where all these regions meet, which looks a little bit singular. But I don't have a full understanding of this.
Questions more? Okay, if not, let's thank speaker again for very interesting
Thank you very much.
lecture.
Yeah, sure. あ、どうぞどうぞどうぞ。はいはい。はいはいはい。はいはい。はいはいはいはい。あ、それですね。多分いい質問ですね。多分なんか。そうですね。ちょっとそのオールペリオンの時とちょっと関係ないかもしれないですけど、多分ファンダメンタルなフェルミオンがあると考えるのと、エニオンとしてフェルミオンが出てくるっていうのがちょっとまず違うんですね。だからファンダメンタルにフェルミオンがあれば、ブレーディングでたまたまフェルミオンが出てくるっていう場合は、そのスピンストラクチャーがなくても、多分エマージェントフェルミオンはいいんだと思うんですね。でただファンダメンタルなフェルミオンがあれば、もちろんフェルミオンがあるからスピンストラクチャーにカップルさせることができて、でフェルミオンだからそれをフェルミオンチャンサイモンセオリーっていうんです。だからフェルミオンチャンサイモンセオリーだから普通にボゾンの TKFT と考えると例えばチャンサイモンのレベルは偶数じゃなきゃいけないとかが出てきて、エマージェントフェルミオンは許されるけど、全体としてはボゾンのセオリーになってるっていう感じで、その場合でもう一つはそのファンダメンタルなフェルミオンがある場合は、そもそもスピンコネクション、スピンストラクチャーにカップしなきゃいけなくて、そのことで K がオッドになるとか、そういうのがありますよね。だからまずそういう違いがあると思う。つまりエニオンとしてなんていうかフラクショナルスタティスティックなんですけど、ファンダメンタルなデグリーっていうのはなんていうんですかね、そういうのを、そもそもなんで区別するのかっていうことなんですけど、それはでもなんか区別しないといけない。エマージェントフェルミオンはそういう NS とかあるっていうのを定義できないって言ったらおかしいですけど、まだ定義しなくて、例えばイジング模型もフェルミオンの10を使って書けますけど、イジング模型として考えるときはボゾンの理論なので、パーティションファンクションは NS と R セクターをサムしなきゃいけなくて、フェルミオンパーティーを保存しなくて、なんかそういう 各々のセクターを考える意味はまあできるけど特にないっていう感じですね。でも一方ジョルダン・ウェグナーとフェルミョンに行けば NSNS とか RR とかそれぞれのセクターからできて、その時はそういう意味があるんだと思う。でもオールフェルミョンっていうのはなんかあれじゃありませんでしたっけ、バウンダリーセールとして出てくるんじゃないですか。だからでバルクボゾンでバウンダリーとしてはフェルミョンが出てくるってやつですね。5次元の方にセカンドシステムプラスとサードシステムプラスの積みたいな、そういう感じのポストにかける。そうですね、そうですね。だからそこでちょっと混乱したのはファンダメンタル性能を考えるべきかそうじゃないかっていう。なんかまあそういう知ってる例としては単にファンダメンタルな自由とした構造を考えればよかったような気がしたんですけど、あとバウンダリーだからそこもちょっと違うような気がするんですけど、まあでも確かにバウンダリーに行ってしまえば NSNS とかあるわけで、いや、ちょっとなんか満足の解明ができないかもしれないです。まあでもファンダメンタルポゾンとファンダメンタルフェルミョンの場合はなんかAnd this disconnect, so let me see how. Let me talk to the people there.
Oh, it's already. Ah, yeah, because they are using this one. Yeah.
Oh.
This is reuse.
Yeah, but we have to use a Zoom.
Yeah.
That's what it is. でもだけど、フェルミョンノートパリティをゲージ化してしまえば、結局、なんていうか。はい。まあ、それノンスピーな場合を考えるってことですね。そうですね。はい。そうしてしまえばっていうことなんですね。そうするとそうだけど、UV コンプリーションが勝手に統計性が強いのとかファンダメンタル。なんかそういう注文とテスコネクトやる。まあ今日の話は基本的に全部ご存と思っていただくのが一番簡単で、まあたまたまフェルミオン的な因縁が出ることもあるけれども、まあフェルミオニックな世界ではない。IR のことやって言ったときに、今で言うとたまたましているので、まあ別にフェルミオンパリティコンサベーションみたいなのがないし、それで UV とまあシムテクステンションの結果。だからまあ、そうですね。왜 얼굴이 뜨지? 아 카메라가 아니라 스크린샷을 해야 하는 거죠? 어떻게다. 콘텐츠 화면. 공유가 된 거죠? 화면 된 거죠? 그건 빼도 돼. 그리고
예, 선사하면 되는 거고. 차지는 100%라서 할 필요 없을 것 같은데.
마이크로 그냥 끝나 있고.
예.
이게 아마 연사가 아니라 누구까지? 이규영 교수님 것이. 네, 이거 비밀번호를 몰라서요.
왜 비밀번호 그런데?
예, 이거 연결해 주시고요. 줌으로 또.
쉐어를 했었는데 아까
네, 이게 대기 모드로 빠지면서
또 다시 집어내야 하는데 됐어 없어. 쉐어. 오케이. 됐어.
thank you. Oops, sorry. Yeah.
Okay, welcome back. We'll continue our session with the third lecture by Marcos Marinho.
So should I use this or? Yeah. Okay. Okay. Thank you very much. so let me first summarize some of the results of yesterday. So the main thing we did yesterday is to introduce one of the basic concepts, which is the concept of transeries. So the idea is that the general formal object or formal power series is of the form, I wrote it like this, phi, z, and then a collection of, so I wrote it like this. So here is the perturbative sector, and these are non-perturbative, all these are actually non-perturbative corrections. And remember that each phi omega is a divergent series. So we have really a collection of, so you have the perturbative series, which is factorially divergent, and then we have all these non-perturbative corrections, which are also given by factorially divergent series. So this is the main object, and this is, in a sense, the way we are going to try to go beyond perturbation theory. If you really want to use perturbation theory and then go beyond it, you have to really go through this formalism. And very important, this is a formal object. This is formal. And in order to get numbers, you need resummation. And we know that the general operation are these lateral Borel resummations. So this is the main conclusion, and let me now make some comments on this. So let me make some comments on transeries, okay? And the first comment is that transeries actually involve at least two small parameters. Two small parameters. So you have the original z, okay, this is a small parameter, and then you will have also small parameters of this form. So e to the -1 over z to some power, okay? And this is very important because this is actually how you go beyond the standard perturbation theory. You have to introduce a new small parameter which is exponentially small. Notice that both of these parameters are small when zeta goes to 0, as long as the real part of this coefficient is positive. These things both go to 0 when z goes to 0. If you want, they both go to 0 when z goes to 0 along the right direction. Okay. Now the second thing is that where do you get? So you see, what you get from perturbation theory is just the first part. Now the question is, where do you get all these things? Now, one of the things that we did in the last 2 days is actually to study a very important source for these non-perturbative corrections, which is from the singularities of the Borel transform. So you take the perturbative series, you look at the singularities, and this is a source of non-perturbative corrections. But it's very important that it's important to notice that to reconstruct observables, you might need more than the phi. You might need additional phi omega. Okay? So the singularities of the Borel transform give you a source of these non-perturbative corrections. But that doesn't mean that they give you all of them. Okay? And there is a kind of simple counterexample. So if you want a simple example that you need more, and these are theories with a theta angle. So this could be, for example, the O3 nonlinear sigma model, Yang-Mills, and so on. So you see, the perturbative, the phi of z is independent of zeta. You know, this is one of the basic truths about theta angles. They are purely non-perturbative in the sense that the perturbative series is totally blind to the value of theta. Okay? But you can have non-perturbative corrections that depend on theta. Okay? For example, if you have a theory in which instantons are well defined, and you have a theta angle, instanton amplitudes, some instanton amplitudes will depend on theta. Okay? So it's clear that phi of z cannot lead to these additional amplitudes that depend on theta, because the singularities of phi of z are also independent of theta. Whatever you find with phi of z, with the perturbative part, is going to be independent of the topological angle. Okay? So that's so in this case, so there are phi omega in these theories, depending on which involving theta dependence, which are invisible in perturbation theory. So which are invisible in particular in the Borel transform of the perturbative series and its singularities. Okay? So actually, using these observations, we distinguish in a paper I wrote with some friends of mine, Lorenzo Di Pietro, Marco Serone, and Sverbeglieri. We actually distinguish between weak and strong forms of resurgence. So in the weak form of resurgence, the only thing you want is observables are resummations of transeries. That's the only thing you require. So observables are going to be given by resummations of transeries, whatever the origin of transeries. Okay. And in the strong version, you have the same thing. Observables are resummations of transeries, and the non-perturbative sectors can be found in perturbation theory. So in the strong version of resurgence, you can reconstruct everything just with perturbation theory. But we know that this is not always the case. I mean, there are many, many objections to this, many situations which is not the case. And one case, for example, is when you have theta angles. Okay? When you have theta angles, definitely it's just impossible to reconstruct everything with perturbation theory because of this dependence on the theta angle. Yes? Gravity. Yes. Let me tell you something. I think we don't really understand well non-perturbative effects even in gauge theories. Okay, even in asymptotically free theories, we don't really understand very well the source of all non-perturbative effects. In the sense that if you want to do perturbation theory and then you want to add exponential small corrections, even in you don't have to go to gravity. You just go to asymptotically free theory. We don't know really how to do this very well. And one corollary of this is that I'm actually quite a little bit surprised about how people working on gravity are so confident about the semi-classical approximation. Because even in gauge theories, which are much better defined, the semi-classical approximation is very complicated. So I have to say that, I think non-perturbative gravity has to be at least as complicated as gauge theories. So I think there is still a lot to discover in terms of non-perturbative effects in gravity. So, one of the things I learned by studying these things is that semi-classical approximations you have to be very skeptical about them. Because we know, and this is one of the things that I will try to explain probably, if not today, tomorrow, there are many non-perturbative effects in gauge theories or in asymptotically free theories which do not really come from semi-classics. So, and these are sometimes the most important non-perturbative effects. So I would suspect that in gravity you will have this and even more. So at least as much as this. So semi-classic has to be taken with a lot of care. Huh? Yes. Sorry, about?
Large M model. There are many large M models. Some large M model can be also instead of the gravity, you can consider large M like based on the holography.
Yes, but again, the large N expansion, it's still divergent, factorially divergent. So each term in the large N expansion is an analytic function. Well, this is not even true for realistic theories, and I will also mention this. But the 1 over n expansion is itself factorially divergent. And it has has some instantons and some non-perturbative corrections which are also very delicate. So it's not completely clear to me that you won't have some kind of very complicated non-perturbative corrections also in the large N expansion. So as I said, you take a large N dual, you might find complicated non-perturbative corrections which are not easily to understand semi-classically. Okay, so the world of non-perturbative corrections is very wild, and that's why in a sense strong resurgence seems to be the norm in the sense that you might find all kinds of things. I mean, we still don't know very well, but things are quite complicated as we go to realistic theories. Now, of course, there are examples where strong resurgence holds. So, for example, in many quantum mechanical examples, you can actually deduce essentially all the non-perturbative sectors by doing this resurgent analysis of the singularities and so on. Okay, very good. So as I said yesterday, this is in a sense the formal setting that we have. And now let's try to do some physics. So let's start with quantum mechanics. So I'm going to start with very simple examples. And these are things which were understood in the 70s, 80s. So this is actually all physics, but not as well known as it should be, I think. So let me actually start discussing quantum mechanics. So what I will do today is I'm going to discuss two examples in quantum mechanics, which are in a sense paradigmatic of the applications of the theory of resurgence. And we will discuss these examples with all the technology that we have used. So I'm going to discuss, this is going to be quantum mechanics in one dimension. If you do quantum mechanics in higher dimensions, things get more complicated. So my examples are going to be quite simple. So I'm going to study the quartic oscillator, which I mentioned at the very beginning of my talks. So this is the quartic oscillator. And I am going to, and you see that in this case, this is in a sense the ideal case for resurgence because you can essentially reconstruct everything by simple Borel resummation. And then I'm going to consider a much more complicated example, which is in a sense the kind of toy model for the lack of Borel summability. Remember that we were saying yesterday that there are situations where your Borel resummation is obstructed because you find singularities in your contour of integration, and this actually blocks your ability to do Borel resummation. And the example of this is actually the double well potential, which I'm going to write in this form. So G over 2, x squared minus 1 over 4G. And the double well is going to illustrate many of the ideas that we presented yesterday, like, for example, the idea that once you have Borel singularities in the integration contour, there are going to be ambiguities, how to remove these ambiguities, how to modify the transeries to include ambiguities and so on, okay? To cancel the ambiguities and so on. Okay, so let's start with the quartic oscillator. Sorry? Yes, absolutely. So let's start with the quartic oscillator. So as I said, this is this was a very, in a sense, one of the founding papers of this story was done by Carl Bender and T.T. Wu in the early 70s. So the question that, early 70s is when quantum field theory starts like getting back to the stage, and then, people start like understanding better Feynman Darans and so on. And the question arises is how the perturbative series behaves. At this time, people were not very sure about how it behaves. Also, there was a very, very remarkable paper by Dyson, okay? So there is a remarkable paper by Dyson of the 50s where actually it's a very nice paper. It has just 1 or 2 pages and maybe 1 equation. And the question that Dyson was asking is the perturbative series in QED convergent or not? And then he gave a very beautiful argument why this couldn't be the case. He said, well, you see, the perturbative series in QD is a series in E squared in the charge of the electron. So, when E squared is positive, you have this perturbative series described in the physics. But it's clear that if you change the sign of E squared, then the physics will be completely different, right? So you cannot have the same function analytic at the origin describing completely different physics. So what he was saying is that there should be mathematically a branch cut somewhere going all the way to 0, which actually tells you that the perturbative series in QED is not convergent, because when you change the sign of the coupling, the physics changes radically. And actually, this argument by Dyson was purely qualitative, and what Bender and Wu did was to make this argument quantitative in the case of the quartic oscillator. So as you see in the discussion, understanding the perturbative series in the quartic oscillator also means understanding what happens when you switch the sign of the coupling, okay? So Bender and Wu actually set up to understand this problem, and they consider the power series in G that you obtain when you do standard stationary perturbation theory, right? So you will get 1/2. So I wrote here many of the terms. 1/2 plus 3G over 4 minus 21G squared over 8 plus blah, blah, blah. And let me actually mention that if you want to play with this series, in one of the files that you can download from my web page, I have 200 terms of this series, the first 200 terms, okay? And this was generated by a wonderful program which was written by Suleiman Patsik and Unsal, which is actually appropriately called the Bender-Wu package. So this is a package in Mathematica which you can use to generate perturbative series in one-dimensional quantum mechanics. So you want to play with resurgence, it's a great package because it generates power series very fast at very large orders. Okay, so Bender and Wu didn't have Mathematica, right? So you are talking about early 70s, but they actually managed to calculate using a computer. They calculate more or less 50 terms of this series. I think something like that, maybe a little bit more. Okay. So So what I did, I like it a lot because it's really experimental mathematics, right? You have all these coefficients, and then you say, well, how this grows? What is the behavior of this? And they recognize immediately that this has factorial behavior, okay? But they were actually able to do something much more precise. So if you write this, again, I mean, I should be precise here. This is not an equality. This is just an asymptotic equality. So if you write this series as ak g to the k, what they found is an actually very precise formula for the asymptotics, which goes like follows. Let me write it because it's a beautiful result in experimental mathematics. 3 to the k. So this is experimental result, okay? Yes, 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 yes. And in the appendix of the notes and in the mathematical package that I give you, that that you can download, you can do, in a sense, this calculation that they did using more terms. Now we can, we made some progress from the 70s to now in terms of computers, but you can essentially do the same calculation that they did. Now, of course, when you do this calculation, this is an example. Remember that when I was discussing these kind of more toy models, you have closed form expressions for the coefficients ak. For example, in this quartic integral, ak was given by a factorial expression and so on. So it was easy to deduce all the properties of these coefficients. But here we don't know. We don't have a closed formula for ak. In most realistic examples in quantum theory, you don't have closed form formula for these coefficients. So what you have is a recursive procedure, which is based on perturbation theory, which allows you to calculate these coefficients, but you don't have a closed form formula for any k. So the only way to understand the asymptotics, if you are not very clever, is to actually, in principle, do first a numerical study. Now I have to say that Bender and Wu were very clever, so they also did an analytic study of the recursion formula for these AK coefficients, and they deduce the asymptotics analytically. So they have an amazing paper, which is not very well known. It's called a Statistical Analysis of Feynman Diagrams, in which they actually deduce the asymptotics from the recursion, okay? But this is something that you probably cannot do in realistic quantum field theories. Now, in any case, they also did that. They actually, from these coefficients, they extracted this. Now, of course, when you do this, you don't get the 3 here, okay? You get a numerical approximation to 3. So instead of 3, you will get 2,999, blah, blah, blah. Instead of 1/2 here, you will get 0.499. And this number, they also got they got a numerical approximation, but they guessed that it was this number. So, and they guessed it right. And there is a paper by Barry Simon, who is this famous mathematician, who was actually astonished that they could guess this number from a numerical approximation to it, right? But there is this idea of Don Zagier that every important number that appears in physics is a combination of pi, square root of 2, square root of 3, and things like that. So you can guess it. If you know that this number is going to be of this form, you can guess it, okay? Anyway, so they get this, and then, now we can use this connection that we found. This is the large order behavior. But what is the large order behavior telling you? Remember that if you take phi 0 and you construct this Borel transform, this asymptotics is going to tell you about the first singularity, the closest singularity to the origin of this Borel transform. Okay? So this formula is equivalent to say that there is going to be a singularity. And you see, remember, the general formula was something like this: s over 2 pi, a to the minus k, and actually, let me write it slightly more general, gamma k plus b. Let me just make sure that I'm using the same notations here. Right, yeah. Okay, sorry. So this is a slightly more general formula that what I was presenting the other day. So this is a general formula when, for large order, when the transseries, when the Borel transform has a branch cut. So this is a case in which you have to enlarge slightly the formalities that I developed so far, and you have to do branch cut. Okay, has a power branch cut with B. Okay, so as I said, this is slightly more general, but you can essentially rederive this formula by using the ingredients that I gave you this day. So, the cases that I was discussing, which is the logarithmic case, is a special case when B is equal to 0. But in general, you have this slightly more general formula. But you can already see that A is the position of the closest singularity, and if you look at the Van-der-Waals formula, it's clear that A is going to be equal to minus 1/3. So this is where the singularity lies. Okay, so you will have a singularity here, and there will be maybe a branch cut here and so on, and then what you also, of course there is a branch cut, because B is the index of the branch cut, and actually here B is equal to 1/2. Okay, so if you now look at what is remember that once you have a singularity, you can zoom the Borel transform in this singularity and extract information. So here there will be a power series also in G, and this is going to be given by 1 over the square root of G, which corresponds to B equal 1/2. So B equal to 1/2 tells you what is going to be the power of G here. And then you have 1 over G over 3. Sorry, 1 over 3G. Okay? And then there are going to be, corrections here that in principle you can also deduce. You can deduce the value of C0, you can deduce the value of C1 by just using this information. Okay? But I'm not going to work out all these things. What I would like to understand is the main pieces appearing here. And in particular, I would like to understand this exponent here. Or if you want, I want to understand why the singularity here is at A equal to minus 1 over 3. Okay? So this is actually, in a sense, what Bender and Wu did. They first derived these asymptotics, and then they asked themselves, what is the physics behind this formula? What is this? We know that this is going on. We know that this perturbative series of the quartic oscillator leads to a singularity here, and there is a new series that appears which goes like e to the 1 over 3G times a non-trivial series in G. So what is the physics of this? That's what they asked. Huh? What is the physics of this series? What is the physical phenomenon which leads to this? What is remember that this should be telling you about a non-perturbative sector, okay? So what is this telling you about the non-perturbative physics of this example? Now the first thing you notice is that this exponential is actually of the wrong sign. But this means that actually this is going to be so this is going to be a small exponential. This is going to be a small exponential if G is negative. And this is very interesting because this gives you a hint that the actual physics in which you will be able to deduce what is going on here is going to involve switching the sign of the coupling constant. And this is exactly the idea of Dyson. If you want to understand a divergent power series, think about what happens if you switch the coupling constant, the value of the coupling constant. So let's try to understand the physics of this problem when you switch the coupling constant, the sign of the coupling constant. So the original problem is very simple, right? You are in standard quantum mechanics, you have a potential which is x squared over 2 plus dx to the 4th. So this is a confining potential, it has only bounded states and so on. But what happens is you switch the sign of the coupling constant. And now G becomes negative, okay? Now let me write G as minus lambda. When here lambda is positive, okay? So I switch the sign of G, so G now is minus something positive. So what will happen is that now the potential will start like quadratic, but at some point the x to the 4th term, which is multiplied by a negative number, will take it down, so you will have a potential like this. Okay? So this is no longer a confining potential. You are not going to have bounded states in this potential. So what happens in this potential is that you will have things which look like bounded states, but eventually will decay. And the physics of this potential is actually very, very interesting. The physics of this potential is tunneling, which is one of the quintessential effects that happens in quantum mechanics. So any particle which is bound here will eventually decay by tunneling effect. Now, a way to make this mathematically precise is that when G is negative, when G is minus lambda, then the ground state energy of a would-be bound state will inherit a small imaginary part. So there will be an imaginary part. Let me write it like this. And we know that this imaginary part is going to be exponentially small because tunneling effects are exponentially small. Tunneling effects are, in a sense, the simplest examples of non-perturbative phenomena in quantum mechanics because they are exponentially small. And you can actually see that the imaginary part of this thing is going to be of the form -1 over lambda. So now we start to understand the physics of this phenomenon because it's exactly this type of exponential that appears in my analysis of the transseries. Yes, you have a question here? Sorry? Not yet. No. Right now, this is not related to Euclidean. Here I'm just really changing the physics of the problem. The Euclidean thing is something that you use with a given potential in order to actually, I'm going to go with Euclidean now, but right now this is the physics potential in the physical potential. So now we are already getting close to this because we are now understanding the value that this exponential term that we see here is the sign of tunneling in the inverted potential. So it's very beautiful. You see, you start with a stable potential, you look at this perturbative series, but you look at the singularity of the Borel transform, so just using perturbation theory, and then you learn about tunneling. You know, this singularity of the Borel transform is telling you that this potential can have non-perturbative tunneling effects when you switch the sign of the coupling constant. That's very beautiful, I think. It's a very beautiful physics example in which you see that these mathematical objects that we have found by doing this kind of very formal complex analysis are really there, are really physical things. Now, how would you actually calculate A? Because if we calculate A, we are going to be able to predict the location of the Borel singularity. So let's try to use non-perturbative physics to actually understand what is the value of A. Now, of course, there are many ways of calculating A. You could do it, for example, a WKB calculation. But we can also do try to interpret this in terms of instantons. Okay? So how you would do this in terms of instantons? This is a way of calculating it. I mean, you could use WKB and forget about instantons. But let's calculate A with instantons. Now, if you want to calculate A with instantons, you have to do this Euclidean rotation of the potential. So you have to do exactly what our friend was telling us. We have to actually go to the inverted potential, but we have to go to the inverted potential of this potential. So in order to do calculation with instantons, we have to go to Euclidean, and this will invert this potential. So what we get is something like this. Okay? So this is the inverted potential. And in this inverted potential, what we have to do is to look for a solution of the classical equations of motions with zero energy. And we want to have zero energy because we don't want to, we want to actually look at the ground state energy, okay? So that's actually, so we have to, it's actually easy to see that there are two solutions doing this. One which goes here, back, goes from the origin to the turning point and back. And then you have the symmetric, the solution that is obtained by symmetry of the potential. Okay, so sometimes people call this a bounce, but I think I call it an instanton because distinguishing between instantons and bounces for me is a little bit. I mean, there is a reason for doing this, but I think it's good to have a general name for everything, and this I call this an instanton. But you know, this is actually something that you can actually write analytically. So here the turning point here is at 2 over square root of 2 over lambda, and the Euclidean solution that you have here, you can find it very easily. It's the square root of 2 over lambda, and then you have 1 over cos of tau minus tau 0. So this is the classical trajectory which represents. So this is a solution of the Euclidean equations of motion. Okay. So now what is the interpretation of A in this formalism? Well, in this formalism, A is just the classical action of this configuration. Okay. Actually, you have to put 1 over lambda because the classical action also depends on lambda. So actually, you can actually check. It's a very easy calculation. Some of the details in the lecture knows that this is 1 over 3 lambda. So we did it. We interpreted the value of this singularity, the location of this singularity, as the action of an instant. Okay? So it's a very beautiful calculation. And in principle, also, I don't know if this calculation has been done in this formalism, but it's an interesting calculation that one could do. One could actually calculate all of the terms of this series, all terms of this series. They could be calculated by doing the expansion of the path integral, the Euclidean path integral, around this instanton solution. You see, when you have a path integral, the instanton solution is the classical saddle point, but then when you do quantum corrections around this configuration, you will get a power series in your coupling constant. And in principle, this would give you all these coefficients, which are the coefficients that control the large order of perturbation theory in the subleading orders in 1 over k. So you see, very beautiful. The instanton solution, you put it in the path integral, you expand around this instanton solution, you have coefficients, and these coefficients are the objects, the mathematical objects that control the asymptotics of a standard perturbation theory around the trivial solution. So this is very similar to what happened in that quartic integral. Remember that in the quartic integral, we had a perturbative series which was obtained by expanding around the trivial saddle point. Okay? And we look at the singularities of the Borel transform of this series, and we found another series. And this series was obtained by expanding the quartic integral around a non-trivial saddle point. So this is the one-dimensional analog of this zero-dimensional phenomenon that we analyze in the quartic integral. The quartic integral is actually the quartic oscillator in 0 dimensions. So this is the one-dimensional version of that zero-dimensional example. Okay? Now, in going from 0 dimensions to 1 dimensions, you go from an ordinary integral to a one-dimensional path integral. Okay? So all the statements that I made in the quartic integral have path integral analogs in 1 dimension. Okay? For quantum mechanics in 1 dimension. Okay? Very good. So actually, if you do a more detailed analysis, you actually can see that there are many, there is a very rich structure of singularities here. So you have a singularity of minus 1/3, but there are also singularities at minus 2/3, minus 3/3, and so on. So the structure of singularities is minus L over 3, where L is a positive integer. Okay? And this should correspond to some sort of analog of multi-instanton configurations. Now, working with multi-instantons directly in the path integral and even finding classical solutions is typically very complicated. It's very, very tricky because you have to kind of put together the solutions and so on. And here there are, I mean, these actually are, as I said, these are bounces, these are unstable instantons and so on. So it's actually quite tricky. And I don't think people have actually studied that directly. But the singularities are there. You can see them. And in principle, you were powerful enough, you could actually extract the multi-instanton singularities from there and so on. So, this is kind of the picture you would have. But summarizing the situation, you could say that for the quartic oscillator, there is a non-trivial structure of Borel singularities, and they have a very clear physical interpretation. They are instantons in the problem with the inverted potential. Okay? Yes? Yes, these are singularities in the Borel transform. So this is the Borel plane of phi not zeta. So we just focus on this one, okay? We just focus on the leading one, but there is actually a sequence of singularities going all the way to infinity in the negative real axis, okay? Well, in principle, you should be able to, in principle, if you have, I mean, there are many ways of extracting this information, but a priori you should look at the Borel transform, and you will find that there are all these singularities, and by expanding around these singularities, you will find branch cuts, and then there will be series attached to these branch cuts, which would give you the multi-instanton amplitude for this instanton number L. Okay. Yes. So what's the question? How? Yes. Yes. Well, that depends on you. You could do it both ways. You could use the local analysis at these singularities to learn about multi-instanton amplitudes, or inversely, you could study multi-instanton amplitudes to learn about the physics of the singularities. There is a relationship between the two. So the way you want to go, that depends a little bit on what you want to do. So people have done it both ways. People have used multi-instanton techniques to understand better these singularities, because understanding these singularities is a difficult problem in complex analysis. And they have done the other way around. They have tried to gather information from these singularities about how the multi-instanton amplitudes look like. So this depends on the problem at hand. Okay. Very good. So, yes. Well, there are many ways of doing it. My favorite one is going to what is called exact WKB method, which will give you this information on the nose. Okay. I mean, mathematically, let's say if you have many, many terms in your series, you could try to guess the leading singularity is easy to get from this large order behavior. But now the subleading singularities are much harder to see, because these are exponential corrections to the asymptotic formula for the AKs. So it becomes very, very complicated, okay? So in practice, this becomes like, much harder. So here you can sort of do some sort of shortcut and do a very beautiful analysis using the WKB method. Here there is something that I haven't exploited yet, which is the Schrödinger equation. So you can exploit the Schrödinger equation to try to get analytic information on these singularities, okay? But if you wanted to do it directly from perturbation theory, it is possible, but it's difficult, okay? Very good. Yes? Yes, that's another consequence. You can actually prove this, again, using WKB, okay? Using WKB, the WKB method can be translated into perturbation theory, and it tells you that these are all the singularities there are. So this is the only singularities there are in this example. There are infinitely many, but these are all they are, okay? Yes? Yes, yeah, I don't know if I would call this a bounce state, but yeah. Oh, yeah. No, this is true. This is true. This is that's true. You should consider the full partition function, and you take the log and so on. So yeah. So this is the structure of the imaginary part of the energy, okay? So it's log of z, and then you would have to take into account all these connected parts and so on. Yes. Okay, so this, in a sense, is one of the aspects. Remember that resurgence has two sides. One side is this analysis. Oh, yes, there is still one question. Sorry, is there? Yes, absolutely. Yeah, this is what I mentioned before. Remember that, let me insist on this. So here, you see that the singularity here involves this 1/2, okay? So this is telling you about the type of singularity. And when you look at the general formula, this is a general formula for a singularity which is a power branch cut, where B is between 0 and 1. So comparing this to this formula, you deduce that B is going to be a 1/2 singularity. Okay? Exactly. The B is very important, this shift of B, because it tells you what kind of singularity you have. If B is 1/2, you have a branch-cut singularity. If B was 0, this would mean a log singularity. Okay? And if B was +1, this would mean a pole singularity. So it's actually so between 0 and 1, okay, you get branch-cut, log, or pole. Okay? So it's very beautiful to see how the nature of the singularity is also encoded in this formula. So remember that resolution has two sides. One side is to actually extract this series and understand the non-perturbative structure. The other thing is, how can we use this information to reconstruct the exact answer? Because of course, you see, I started with this formal power series, but this thing, the energy, the ground state energy as a function of G, is a well-defined function for positive G. So if you give me a value of G, spectral theory tells me that the ground state energy is going to be a strictly positive number. Okay, so there is a ground state here with an energy E0 of G, which is strictly positive for any positive G. Okay, so the question is, can we reconstruct this exact number from this information? Well, this is a case in which we are lucky. And why are we lucky? Because you see, if we want to reconstruct this ground state energy for positive G, then positive G is here. So it's not in a Stokes ray, because the Stokes ray here, remember, the Stokes ray is the ray that goes through the singularity. So the Stokes ray here is actually the negative real axis. This is the Stokes ray, okay? So it's nice because this means, already from this analysis, we know that the Borel resummation of phi 0 of G, which is this thing, is actually well defined. Well, barring some bath growth of this thing, but there are no obstructions in terms of singularity. So this is actually, one can prove mathematically, can prove rigorously, that this is well defined. So here the Borel resummation is perfectly well defined. We know that there are not going to be obstructions from singularities, and moreover, we have this beautiful result that actually this Borel resummation is equal to E0 of G. Okay? So exactly. So you can, and this is a theorem of Grecki, Simon, maybe other people. So it's something that was proved in the 70s, that you can actually get the exact ground state energy by Borel resummation. And you don't need anything else, okay? Well, no, this is for positive G. This is for positive G, yeah. Now, for negative G, it's more complicated. You can study this when G is negative, and then you have to do some analytic continuations and so on. And of course, the thing is that when G is negative, the problem is that the bound state problem is not really well defined in quantum mechanics, because you see, when G is negative, you are considering this potential. So here you cannot compute bound state energy. You can compute resonances. Resonances are things with imaginary part. And I think in this case you can also, and then of course, what is going to happen is that this ground state energy will have a branch cut around the negative real axis, okay? So you cannot really compute the ground state energy when G is strictly negative, because you are on top of the branch cut, okay? But away from the branch cut, I think this statement is still true. Away from the branch cut, this is still true. It's actually the same as for the quartic integral. The quartic integral, remember, we also had this thing that the integral itself could be reproduced from the resummation of the perturbative series, and the same thing happens here. And I think this is, I'm not completely sure, but I think this can be extended to G in the complex plane minus the negative real axis. This might be true. Huh? It's definitely true for the quartic integral, and I think this is also might be true. Okay. Okay, very good. So this is really a success story, and notice that you don't need trans-series here. Here you only need the perturbative series. And actually, you could see that here the trans-series, I mean the additional non-perturbative corrections that we got from these singularities cannot do the job here of doing a correction. Why? Because precisely these things give me a positive exponential, you see? So when G is positive, if there were corrections for the series, they would be exponentially enhanced, not exponentially suppressed. So when you have these exponentially enhanced corrections, then, it's very, you don't expect anything coming from there, because you know that, the exact energy still has the property that this asymptotic expansion near G equals 0 is given by the perturbative series. So any exponentially enhanced correction to that would completely destroy this property. Okay, so when there are these Borel singularities on the negative real axis, this means that you really shouldn't worry about them, and then you can go ahead and equate your exact result to the Borel resummation of the perturbative series. Okay. Yes. That's a very good question. That's what I tell you here, that there is a branch cut. So what happens is the following. What happens is that when you do the resummation on the negative, when G is negative, you will have to tell me if you do the Borel resummation on top or below. But it's actually okay, because the problem that we are trying to define is a problem of resonances. The energy of a resonance has an imaginary part which is not well defined up to a sign. The imaginary part of a resonance is not a well-defined problem. Remember that when you do this analytic continuation of the energies of this problem to the negative values of G, there is going to be a branch cut. So precisely the two choices of Borel resummation means that there is a discontinuity through the cut. But this is precisely the physics of a resonance, you see? No, what I'm saying is that if you want to do this, imagine that now you want to do this for negative, okay? So you wanted to do this for negative, you will have to choose a sign for this, okay? Right? You will have to choose a choice of resummation, because you see, in this case, you will have, this will be through the negative real axis, so the Stokes ray. And then, so it will be the Stokes ray plus minus. You can, sorry, not the Stokes ray, sorry. You will have to do it, you will have to do here the resummation C plus minus that we were defining, C plus minus pi. So here, okay. So this is the formula that you would get for G negative, okay? So for G negative, this Borel resummation is not well defined, because you have to do a choice of Borel resummation. But in this case, the ambiguity here is not an ambiguity because you are lacking information. This ambiguity is intrinsic to the problem, because when the quartic oscillator, you put the coupling to be negative, there is not going to be a well-defined energy. There are going to be only resonances, and resonances are ill-defined. The imaginary part of a resonance is only defined up to a sign. So the two choices of Borel resummation are exactly the ones that correspond to this problem. It's not because you are lacking physics. It's because the problem is intrinsically ill-defined. You have a bound state, you have a potential with bound states, and then you take it down to minus infinity by switching the sign. Your problem of bound states is no longer well defined. Yes, but this is precisely because you have a branch cut in the exact energy. The function E0 of G has a branch cut on the negative real axis. So this means that there are going to be two choices for this function. Of course, yeah, branch cut is at two choices, yes. No, but I mean, but this, let's not go back. We had this discussion yesterday. There is a branch cut. So what you want, the physical question you can ask is what is the discontinuity through this branch cut? And this is precisely the formula that I was saying yesterday. The discontinuity through this branch cut will be the contribution from all these singularities, okay? But there is, Now, what I'm saying is just very simple. What I'm saying is that imaginary of there is E0. E0 of G has a branch cut. The exact energy has a branch cut along the negative real axis. So what I'm saying is that the discontinuity of E0, which is something that you can compute exactly in quantum mechanics by doing appropriate analytic continuation, is the discontinuity of S plus minus. It's the discontinuity of what we call discontinuity of phi 0. Okay? This is the statement I want to make. And this is a physical statement. This is an exact quantity. And this is what we obtain by resurgence, okay? Plus resummation. So, but what is very important here is that here, the fact that there is an ambiguity when you go to a negative real axis is not telling you that your physics, that the information in your strand series is in your phi 0 is incomplete. It's not telling you this, because the physics itself has this discontinuity. You see, I told you, I was telling you yesterday that when you have singularities, this might mean that your perturbative series only leads you to a good result modulo an ambiguity. And this ambiguity might mean that you are missing ingredients, but not here. Here the fact that there are two lateral resummations is not because you are missing physics. It's not that you have to cure this. We are going to see now an example of the double well in which this is an indication of lacking information, but here is not. Here the fact that there are two lateral resummations is precisely mimicking the fact that the exact ground state energy has a physical branch cut, okay? And the resummed phi 0, the two lateral resummations are exactly giving you the information that you need in order to understand this branch cut, okay? Okay. Very good. So now, let's see, what time is it? Okay, so I have half an hour or? Yeah, okay. So now let's go to the double well. Now there are, you can do the same thing. So you have here, so the double well has this structure, right? And then what you want to do is perturbation theory. And in perturbation theory, you expand around any of these vacuum. These vacuum in perturbation theory are completely equivalent. So you can actually calculate A0 of G through a power series. And then what you're going to find is a very similar series. So, well, not very similar, superficially similar. Minus, so I wrote here some terms of this series. And again, in the file that you can download from my webpage, there are 200 terms of this series, again, using this Vanderbu package of Suleiman Pasik and Unsal. And then with this series, you can now, again, ask the same questions, okay? Where are the singularities, and so on and so forth. Well, so let me tell you what you find. So let's call this series phi 0 of G again. I'm just going to use the same name and notations, but of course here I'm working on a different example. And if you look at the Borel plane of its Borel transform, what you find is that now the singularity is on the positive real axis, okay? And it's a 1/3, okay? So now there is going to be a singularity here. And actually you can find experimentally this type of result, okay? And this type of result was, I think, I don't know who was the first person to find this, but there is a paper by Brezan, Parisi, and Saint-Justin where they actually look at this. And I think they were the first ones maybe to predict this asymptotic behavior, okay? So again, in one of the programs that you can download from my webpage, there is going to be the same type of calculations that are done for the quartic oscillator for this double well potential, okay? So Now, the physics is very different. And then if you think about the series that is associated to this singularity, that is called phi over 1/3g, then you find that you get actually 1 over g times e to the minus 1 over 3g times corrections, okay? So here actually the fact that you have a k factorial means that you will have a pole in the transseries, and this is what I wrote here, okay? And then there will be a log singularity. So this is a pole plus a log singularity, okay? In this case, the large order behavior tells you, again, the structure of the singularity, which is a pole plus a log branch cut, okay? Yes? Oh, sorry. Yes, without hat, yeah. No, sorry, there is a notation thing here that I'm including here the exponential piece already, okay? So maybe I should change my notation. You're right, actually in my notes I correct them. So let's actually write this as phi, capital Phi, which is e to the minus 1 over 3g times the small phi, okay? So I just add the exponential part, okay? So remember that near the singularity you can extract a series which is factorially divergent, and then this is what appears here, and then I added the exponential by hand because remember that when you calculate discontinuities, the exponentials appear naturally. So this is natural to put all these things together with exponential, and remember that in physical calculations you get this exponential, right? That's what you get in instanton calculus, or when we did the saddle point expansion of the quartic integral. In physical calculations, this transseries always come with an exponential which reflects the location of the singularity, okay? 1 of g factor is because of this. This is, you should go to my notes. This is k factorial. This means that this is gamma of k plus 1, and this is related to the fact that there is a pole here so this singularity is a pole plus a logarithmic branch cut, and then you will have to add a pole in the transseries here. You have a power 1 over g, okay? This I mentioned yesterday, maybe a little bit fast, but I was telling you that when the singularity was of the form minus s times a over 2 pi, 1 over xi, then the transseries here yes, so should actually have a over sorry, this is zeta, or xi. This would be phi xi plus blah blah blah, and then this would give phi omega of zeta, which is a over zeta, blah blah blah. So when there is a pole in the Borel transform, you have to include this will lead to a pole in the phi omega, okay? And why do we know that there is a pole here? Because this factorial behavior tells you that there is a pole, okay? And also there is a log branch cut. So this singularity is a mix of a pole and a branch cut, okay? Okay, so, but actually we want to include these powers because 1 over g is actually a physical fact. I mean, when we try to reproduce this with an instanton calculation, 1 over g will be there, okay? So that's, I'm not going to do this calculation, but if you did an instanton calculation, including the one loop correction to the instanton, you would see this 1 over g, okay? Everything that you get from the singularity analysis, you can reproduce it in these cases through an instanton calculation, including 1 over g, okay? And remember, in the quartic case, I mentioned that there was here 1 over the square root of g, okay? This thing here also came from the general rule to include to construct transseries from the branch cut, and this is also physical. This 1 over the square root of g is what you would obtain in an instanton calculation when you include the prefactor of the instanton. Here I only calculated the action of the instanton, but if you do a one loop calculation of the instanton, you also get 1 over the square root of g. So these factors are physical, okay? The rules, I define some rules to put these factors, depending on the type of singularity, but these rules are motivated physically, okay? Yes, because this singularity, that's a good question. Because there are subleading terms in the asymptotics. If there was no subleading terms in the asymptotics, that would mean that it's just a simple pole. But because this asymptotics doesn't finish here because it has 1 over k corrections, this means that there has to be something more here. Okay. Okay. So the asymptotics tells you everything. Okay. But you are right. If there was only a pole, then the asymptotics will be exactly given by this. So here, if I have an equality sign here, so this, just an equality sign, then I wouldn't have corrections here. This would be just e to the minus 1 over 3g times 1 over g. Okay. But since this is an approximate expression for the leading behavior when k is large, I know that it must be something else than just the pole. And this is going to be a logarithmic branch cut. Okay. Yes, yes, that's a good question. So this is what you find from large order analysis, which, remember that large order analysis, in the way I presented, so in the sort of most elementary way, only gives you the leading singularity. But of course, this doesn't preclude the existence of more singularity, and indeed, there are going to be more singularities at 2/3, 1, and so on. So you have also an integer sequence of singularities here, okay? Okay, very good. So now, remember that what we did for the quartic oscillator was to interpret this series in terms of instanton physics. So can we do the same thing here? Can we actually understand this from instanton physics? And indeed we can, but this is a little bit more subtle. Because what happens is the following. Of course, we all know that the double well is the prototypical example of instanton physics. And if you want to consider instantons here, again, you have to do these inverse potentials. And when you do this inverse potential, you know that there is an instanton here. There is a one instanton solution which goes from here to here. Okay? So this is the instanton solution that you find in many books. And you can actually find the solution explicitly. So you are working in Euclidean time. So let me write this as, so here, again, you can have 1 over 2 square root of g, a tanh. So this is the exact, this is a solution of the Euclidean equations of motion. And then, you can now compute the action, okay? But it turns out that the classical action of this thing is actually 1 over 6 times g, okay? So it's half, okay, of this. And notice that this doesn't lead to any singularity. So the one instanton sector here doesn't appear as a singularity in the Borel plane, okay? So the one instanton does not appear as a singularity. And in a sense, this is in a sense a sort of is related to this theta angle thing, okay? Because what happens here is that you don't have a theta angle, but you have sort of Z2 theta angle, okay? So essentially, instantons that go instantons or anti-instantons are not going to be detected by the Borel analysis. What is going to be detected are instanton anti-instantons. So things that go from here and back. So this is what explains these things. And so here, so the singularity at zeta equal to 1 over third is an instanton anti-instanton effect, okay? So that's a little bit more subtle than what we had before, but in a sense, it's an example of this phenomenon that you have not every instanton, not every non-perturbative sector will appear in your Borel plane, okay? So here only things we have zero charge, if you want, appear, okay? Now the question that arises is how you reconstruct now the exact ground state energy. So do you want, again, the double well potential is an example in which the ground state energy is a well-defined object. This is a confining potential. So the ground state energy is a well-defined quantity for positive G, and you would like to compute it from perturbation theory. Now here is where you really see the problems of lack of Borel summability, because because now the positive real axis is a Stokes ray. So now, if you try to do your integral here, when you try to do the integral here, you're going to hit all these singularities. So there is no way that the Borel resummation, the conventional one, is well defined. So the best you can do is to do a lateral resummation. So you can do S plus minus phi 0 G, but of course this will have an imaginary part, okay? And this is actually the first case in which you have a highly non-trivial phenomenon of transeries. So it turns out that you can construct a transeries that actually leads to the exact ground state energy. And this transeries has various pieces. So you will have the perturbative piece, phi 0 of G. Then, let me put it a minus sign, but you will have an additional piece, phi 1 over G, phi 1 G, that corresponds to one instanton. And as I said before, this piece does not appear by a Borel analysis. So this is actually an example of what I was mentioning before, that if you really want to reconstruct your exact observable, you might need more stuff than what you find from a Borel analysis. So this is a one instanton piece that has to be added by hand, in a sense. It's not something that you found from the singularities. And now comes the two instanton piece. Now the two instanton piece is very interesting because it will have two pieces. You will have the two instanton piece real, and then you will have an imaginary piece, C plus minus phi 2, let me call it imaginary. Let me stop here for the moment being. And so this is the big transeries for, and then there will be higher order corrections. So you can actually, it's of course possible to write a closed formula for all this, but let me just discuss what we have here. So we have a one instanton piece which is actually crucial. And one of the reasons why it's crucial is the following. You see, the double well has this property that perturbation theory is even wrong qualitatively. Because according to perturbation theory, in the double well, there should be always two ground states, which are the generating energy. Perturbation theory doesn't distinguish these two ground states. So perturbation theory tells you that there is a ground state located at the left minimum and a ground state located at the right minimum, and they have the same energy. But we know that this is qualitatively wrong, because the actual ground, there is actually one single ground state, and it's known that it's instantons which actually remove this degeneracy. So you need this instanton effect here just to remove the degeneracy. And I put a minus sign because this is actually what decreases the energy to the ground state. If you put a plus sign, you will get the energy of the first excited ground state. Okay? So this one instanton is actually the difference, the energy gap between the ground state and the first excited state. It's purely non-perturbative, it's a one instanton effect. Now, there will be two instanton effects. And that's very interesting because there is one piece which is formally real, and there is one piece which is formally imaginary. So imagine that you want to resound this expression here. So if you want to resound this expression, you will have to add S plus minus of phi 0, G. Then you have the instanton piece. Then you have the two instanton piece. But then at some point you have this imaginary piece, C plus minus, and then you will have S plus minus phi 2 of G, what I call phi 2 imaginary. Let me. Okay? Now, this thing, what is this thing? This thing will have a real part, which is the same for both signs. And then it will have an imaginary part, which is essentially half the discontinuity. And we know that this part is of order e to the minus 1 over 3g. We know that this imaginary part is of this order. Okay? But this is actually the coefficient, this is actually the weight, the strength of the two instanton part. The two instanton part will have e to the minus 1 over 3g times a series, right? Which I'm not going to write in detail. You can actually find it in the notes. And then what happens is that here you have then, let me actually try to make this clear, because this is actually the kind of simplest example of this cancellation that I mentioned. So here you have an imaginary piece which you don't like, because we know that the energy of the ground state of the double well is real. So you have this piece that you don't like, which came from perturbative theory, from perturbation theory. And then you have this imaginary piece coming from the two instanton. And then you see the choices of plus minus essentially give you here a plus minus choice. And you can actually now, you can actually see that this thing is exactly equal to the discontinuity, so you can actually cancel these two things. So you choose S plus, you will have to take C plus, say, to be 1. And you choose S minus, you will have to choose C minus to be, say, minus 1. So this is exactly how this mechanism works here. And it's actually very non-trivial. You see, you can actually write the ground state energy as an exact resounding series, but then the perturbative part will give you imaginary ambiguities that you don't want, and you have to cancel them explicitly by adding two instanton corrections. And one also important thing about this, and this is something that people always ask me, says, but look, how is it possible that the transseries, that this is, which is supposed to is the transseries for the ground state energy, has imaginary parts? Okay. Well, that's the point. Precisely because a transseries is a formal object that you have to make sense of by doing Borel resummation, the formal expression has imaginary parts. Okay? And this is actually a source of confusion. When you read about instantons, you see that they come from imaginary pieces, and sometimes people, when they see an imaginary piece, they say, oh, instability, instability. No, careful. An imaginary piece doesn't mean that your system is unstable. There is nothing more stable than the ground state of the double well. And still, its transseries has an imaginary piece. So it's not true that every imaginary instanton effect is a signal of instability. You can have imaginary instanton effects because you are looking at a non-Borel summable series, and you have to cancel these singularities by adding imaginary pieces explicitly. And it's only when you do Borel resummation that all these pieces will cancel. Okay? And you can actually do a kind of very detailed numerical checks that this is actually what happens, that these things cancel explicitly, and that's something that you can, as I said, you can check very explicitly. Okay, and so this is actually how transseries work. I mean, here you are not so lucky that the perturbative series gives you everything. Okay. Because there is no non-trivial physics that is appearing, and this is the physics of instantons. But still, you can actually write an explicit expression involving instanton corrections which reconstruct the exact answer. And this is actually important because at some point, I think many years ago, when people found that there were Borel singularities, they would say, oh, the perturbation theory is non-Borel summable, so I close my book and I do something else. And this is actually not this is not completely right, because even if there are Borel singularities, even if the Borel resummation is obstructed, you can do lateral Borel resummations and add all these corrections to get something which is at the end of the day the exact result. Okay, so that's in a sense a very important example, and is the model for many examples that people have seen. For many examples that which are much more complicated, which are, for example, examples in gauge theory, examples in quantum field theory, or examples in string theory, in which we know that there are going to be singularities in the Borel plane, in the positive real axis, or somewhere else, and then we shouldn't be stopped of trying to push this program of transseries by the appearance of Borel singularities. What you have to do is to find the non-perturbative corrections that are going to correct for this, that are going to actually give you an exact result at the end of the day. Okay? But I think I have 7 minutes, right? This is until 1:45. Okay, so So are there questions on this? And I think this, in a sense, the most important part of what I said. If you already understood these two examples in quantum mechanics, that's already very good, because these are things that you are probably studied at some point in undergraduate or graduate school, and this is actually the right way of doing them. so this is already quite good. Yes? No. Here, in which sense Borel resemble? In the sense that there will be singularity. I mean, there will be. Yeah. So actually, this guy here is going to be also a non-Borel resummable series. So when you do, it's a very interesting. There is a kind of cancellation pattern. So phi 1. So let me change color here. Phi 1 is of the form, actually I wrote it here, is of the form 1 over square root of g, e to the minus 1 over 3g, and then this is multiplied by a series, and this series is non-Borel summable. Sorry? No, this is the one instanton. This is one of, sorry, you're right, sorry, you're absolutely right, sorry. Saying something stupid. Yeah, absolutely. This is 1 over 6g. Sorry. Sorry, I'm making us, sorry. This is 3. You see, factors of 2 are our worst nightmares, right? Yes, this is 1 over 6, thank you. So this series is non-Borel summable. So when you resum this series, you will get imaginary, so it will give you an imaginary ambiguity. Which I remember correctly is 1 over minus, it has the minus 1 over 6g from the prefactor times the intrinsic ambiguity of these things, which is minus 1 over 3g. So the imaginary ambiguity of the one instanton amplitude is a 3 instanton amplitude. So when you add the 3 instanton, you will have to cancel the ambiguity that comes from the perturbative sector and the one that it comes from the one instanton sector. So you push the instanton calculus, you have to make sure that you cancel every ambiguity that comes from behind. Of course, here it looks a little bit like, clumsy that I'm doing it this way. You can actually prove, that lateral resummations completely agree. Both lateral resummations completely agree when you add, when you use, when you write the exact formula. Okay, but there is a kind of sequence of cancellations, and everything cancels the ambiguities that you had before. But of course, the cancellation always happens at higher instanton number. So you have to, the work of higher instantons is to give you real corrections, but also to cancel the imaginary ambiguities. Okay? But it's also important that instantons are not just there to cancel ambiguities. They also have their own real part, and this is also important. I mean, just canceling ambiguities would be a very silly role for the instantons. They do this, but they also give you a real contribution. Okay, so you have to take into account both things. Yeah, but that's in a sense this sequence of cancellations, which goes all the way through the instanton chain, which eventually you have to actually verify in detail. Okay. Yes. Yes. Yes, that's very good. That's a very good question. I can hear you. Yes. No real saddle. Well, the thing is that, it's true that if you want to interpret this correction as an instanton and an instanton correction, there is this true story that it's true that there is no actual solution of the equations of motion, which is a instanton anti-instanton. That's no. So you have to do something very complicated. You have to do what is called a pseudo-instanton solution. So you have to take an instanton anti-instanton, put them very far apart, and then get them closer and closer. And this is true that this is just an approximate solution to the equations of motion. And then you have to work through this. But I don't think this is actually related to the fact that there is a singularity or not, because you can do this calculation in WKB, where things are a little bit more abstract, and you don't really insist in attaching everything you get to a contribution of the path integral, and you see that this ambiguity is still there. Okay, but it's true. What the way I interpret this is that multi-instanton calculus is a mess. Okay, and then you have to use all. That's what I'm saying. You know, semi-classics is very tricky. I mean, it's not so easy. So already when you are trying to interpret this calculation in terms of semi-classic, you have to do this kind of complicate you have to actually use configurations which are not real, not actual saddle points of the axiom, okay, and try to reinterpret your exponential correction, which is there, in terms of this object, okay. That's why I think this is really this means that multi-instanton calculus is generically so it's here, right? No. How do I get back to? Sorry. Okay. Okay.
No.
Yeah.
I guess sharing is not disconnected. Oh, then
But anyway, I think we are reaching already. I mean, I think I'm not going to do more today, so I think maybe probably getting questions is probably more interesting because.
yeah, okay.
Okay, very good. Yes.
Yeah, you can go with.
Sorry? Yes, yes. Yes, yes. But as I said, you know, since you can do this calculation, yeah, I mean, that's true. What you how is saying is that when you do the two instanton and instanton calculation, they see that it has also some intrinsic ambiguity because, you know, the instanton gas is not well defined for positive coupling constant and so on. And then, you know, this could be related to the Borel ambiguity. This is this Bogomolny-Saint-Just interpretation. But on the other hand, if you do the calculation in exact WKB, you don't see any of this. You see a sequence of singularities, right? And the calculation has a different flavor in a sense. So sometimes, you know, I wonder if this kind of multi-instant interpretation is more like, you know, it's more like in the eye of the beholder, in the sense that, you know, you are trying to interpret all these corrections in terms of semi-classical configurations, and then you are in a sense putting this, you know, forcing a little bit the interpretation in terms of semi-classical configurations. But it's true, yeah. It's true that there is an ambiguity in the multi-instanton calculation, which corresponds to the ambiguity in the Borel transform. And this, some people say that this is, you know, a natural way of explaining the cancellation. Okay, this Bogomolny-Saint-Just mechanism. But then, you know, if you try to push this to higher order instantons, things become very messy. Things become very messy. So what I like about WKB method is that you get the exact result without having to do anything. So you just get, so you lack the interpretation in terms of path integral, but you get something which is completely equivalent and exact. Yes? Yes. Yes, that you could say that this is ambiguous. Yeah, in the sense that it's ambiguous, but when you use all this machinery, when you use the machinery of Borel resumation and so on and so forth, okay? Yeah, no, I think scheme dependence is slightly different. This is an additional ambiguity in quantum field theory, right? So in quantum field theory, even when you make a choice of a scheme, you will find these ambiguities in the resumation. So yeah. Yeah, but in that sense, you can think about this as ambiguity in how I split perturbation theory. I don't know. This is a metaphorical way of speaking. But yeah, you could say that, you know, the perturbative and the two instanton part get mixed through this ambiguity cancellation. Yes, you could say that. Yeah. But I have to say that in general, in quantum field theory, it's not instantons who do this job of canceling ambiguities. It's this new object called renormalon. So renormalons do not have a semi-classical interpretation in general. So it makes this thing much more complicated. Okay, so.
Are there further questions?
Actually, I saw some question in the chat. I'm not sure if we asked, but I remember the question was this two-instance solution that you write contribution. Is it instanton and anti-instanton?
Yes, when I mean two instantons here, I mean yeah, this is more precisely this imaginary part. This is an instanton, anti-instanton. Yes. I mean, there is this story that Gerald Yoon and Mita Nunsal call the resurgence triangle. That they say that there is some sort of selection rule that tells you that if you want to cancel an ambiguity in perturbation theory, you have to use instanton and anti-instanton configuration, not pure instanton or pure anti-instanton configuration. So in this case, this is exactly what happens, and this is an instanton anti-instanton configuration. Okay.
Can I have
Yes, yes.
So far, you only talk about this ground state energy.
Yes, yes.
Is there some other observable that you can apply this resurgence?
Yes, of course you can do this for any arbitrary energy level. Huh? So all these considerations all the spectrum you can do it. Now you could now consider correlation functions, okay? And there were actually recent work by Saint-Just, Parisi, and company on correlation functions. So you can also do this analysis in correlation functions, but things get a little bit more complicated. So this has been less explored, even in quantum mechanics, okay?
Yeah, in that case, the coefficient probably relate to if that is quantum mechanics, some function of time. It's not the number, right?
Yes, absolutely. Yeah, absolutely. Very often, here I'm considering, in a sense, the simplest case of resurgence in which the series are numerical. So every coefficient in your coupling constant is a number. But this is actually not the most general case. Generally, what you have are series in a coupling constant which themselves depend on parameters. And this is what is called sometimes parametric resurgence. This is actually important because this is what happens sometimes in, for example, in quantum field theory, in string theory. You have typically this, for example, you consider the string perturbative series, the coefficients are functions of the moduli of the model of the theory. So you have generically this situation. Now, this introduces many interesting things because now the position of the singularities depend on the value of the moduli. So they move in moduli space. As you vary your moduli, the structure of singularities moves, and sometimes they can even change discontinuously. And this is this famous wall-crossing mechanism that the structure of singularities can jump discontinuously as you move in moduli space, and so on. So there are many new phenomena for parametric resurgence, but I won't consider parametric resurgence in these talks.
If there are no more questions, let's thank Marcos.
All right, so for lunch, again, with your name tag, you can go into the cafeteria. And another one is that maybe you got the email that there are still COVID infection floating around in here, and some people got infected. And you should let us know as soon as you got that, and also isolate yourself in hotel. Okay.
Good.
but there was some problem in the this light. For light, because yesterday done. There was some problem in the main border. So is it okay to write out in the side?
Sure.
Sorry about it so much.
That's okay. Yeah.
But I will connect soon. But I have to find someone who has connected. Give me a second. So I heard that there's something wrong with this lighting.
Yes. He just told me. So we have to use this, right?
Would it be okay?
Yeah, I could make that work.
Okay.
Do you know how to access it? Do we?
I don't know. Maybe you can. Oh, no. Start.
I think someone just went to find out.
Okay.
Okay. Yeah, that should work.
Oh, will you using your?
I would prefer to use this as big notes and maybe write on this. Does that
Right
work?
on this? Oh, okay, yeah, sure. Will you using this one or which one do you prefer?
Yeah, I'll use the headset.
Headset, okay.
That'll work. 평소에 쓰시는 거.
네. So you prefer the white, right? That's
Yes,
white.
that'd be good.
And, so, it will be up here soon.
Okay, I will start writing.
And would taking the blackboard to the front will work better because you can get the lighting from the hole. Alright? You know, the writing on the blackboard looks darker if we push it in. But if we take it, because this lighting. this light is off, but if you know, I could barely see what Shinsei wrote, but if you take it more fronter, we can get light from these and maybe it gets brighter. That's possible. But itself, is it? I mean,
I mean, to me, reading is okay, but
yeah.
I'm just wondering some lecturers might prefer still Because I hear that problem will continue till next Monday, right?
Yes.
So yeah. Triachi said that he will prepare a slide or something because he was unsure about the black hole condition. It seemed that Benini wanted the black hole. Well, we can still ask him to write here. Yeah. 해보셨어요?
마이너스까지는 안 돼.
막 그림은 떨어지니까 안 되겠죠.
조명 중에 여기 클레로 꽂아서 이렇게 위에서 패널이 있잖아요.
동굴감이 좀 미저러블하긴 하다. 외곽적이 나왔어요.
여기가 보드가 컨트롤하는 보드가
이번 학기 끝날 때까지 계속 이게 안 되는 거야?
예, 이거 앞에 거. 그러니까 요거는 괜찮아요. 컨트롤이
조치만 하면 되는 거 아니에요?
이게 가는 게 아니고 컨트롤을
뭐 있어? 펜처럼 생긴 거 말이죠? 이게 약간
그것도 반응을 좀 요새 보시면 여기 책상 같은 데 이렇게 클립으로
예.
꽂아서 그거를 실판에 이렇게 꽂아서
그게 있어요? 뭐 해야 되는 거야? 보기는 웃기지만 사실 그거는 충분할 수도 있긴 하네.
나오게 보니까 되게 다르게
음악 따라 다 까지나? 정확히 뭘 써야 되는지. 그냥 이렇게 클립 있고 이렇게 여기 이렇게 두개 쓰는 게 있고 쓰면 되죠. 전기는 어디서 쓰고 음악 따라
이게 그것도 있단 말이죠. LED 이거 있고
하나씩만 있으면 되는 칠판에 두개 쓰면
이제 테스트를 해가지고 제품화가 그렇게 된다는 보장이 지금 그냥 일단 아이디어는
오늘 이만 따라 가볼래? 이만큼 있어 볼게. 큰 마트나 조명 이거 좀 사고. 조명 뭐
불이 나와요.
여기가 안 좋은데 칠판 쓰기가 힘들어. 신세이가 쓰다가 바꿨잖아요. 오늘 아침에 바꿨거든요. 큰 마트 같은 거 없어요? 그냥 그 조명기구 같은 거. 차 갖고 와보는 거야. 내가 마음대로 사면 돼.
Yeah. Yeah, it's good.
using this head mic, right?
Yes.
Chris will give his third lecture, please.
Hi, welcome back. So last time, in our pursuit of understanding the ADS-CFT dictionary, what we saw was what we called Theorem 1, originally written down in its final form by Daniel Harlow in 2016. And Theorem 1 essentially told us that that two conditions were equivalent. One was a reconstruction statement about what a certain bulk boundary subregion could reconstruct, what region of the bulk. And then the second one was a statement like the quantum extremal surface formula. And so the fact that they were equivalent told us that if you have some subregion of a CFT with a holographic dual, it can reconstruct exactly its entanglement wedge, which is the region up to its quantum extremal surface. But now, remember, this was all in the context of these fixed QES subspaces, which are subspaces of the Bulk-Hilbert space in which the position of the quantum extremal surface, gamma, was independent of the state. So for example, if you were considering vacuum ADS and some perturbations on top of that. So we have not yet considered the full range of ADS states that we're interested in, say from vacuum to black hole states, just these fixed QES subspaces for now. And this lecture will generalize from that. But we saw that given this theorem, we actually learned something remarkably interesting about how ADS is encoded into the CFT. And it was this. So we considered a setup like this one, where we divided the boundary into thirds, A, B, and C, and we were considering some bulk operator phi in the middle. And we, if we considered, say, AB, the union of A and B here, as the CFT subregion of interest, its quantum extremal surface, you can just directly evaluate, would be this one here. We'll call this gamma. And so it would include this point where phi is acting in the entanglement wedge. And so that would cause us, by theorem 1, to say, okay, on AB there exists an operator, OAB, that reconstructs this operator phi. So, and then likewise, from the symmetry of the problem, you can convince yourself also there's an operator on BC that we'll call OBC that also reconstructs phi, and an operator on AC that also reconstructs phi. So they all act like the same bulk operator, at least in this fixed QES subspace. But we argued that they actually can't be the same operator because then they would all have to be trivial. Because they don't all have support on every region, right? So the intersection of their support is 0. And Okay, so you have these three operators that are all different as CFT operators, but they all purport to act like the same bulk operator, at least in this subspace. And this tells us what's come to be known as the language. Yeah, in the language that people use nowadays, this tells us the lesson that ADS physics is encoded into the CFT physics like a quantum error correcting code. And I want to explain that a little bit by giving you the canonical example of this. It's a very simple quantum error correcting code that will resemble this setup, in fact, and I think gives a lot of intuition for what it means for something to be encoded like a quantum error correcting code. And this is an important lesson because, remember, this is our goal, understanding how ADS physics is embedded in CFT physics. So the example is this one. So it's called the 3-qubit code. So a qubit, if you're unfamiliar, it's a quantum system with a 3-dimensional Hilbert space. So it's like a qubit, but instead of being a bit because it's 2, it's a trit because it's 3. It's a qubit. So there's one qubit that we'll call little q, and this is often called the logical Hilbert space. HQ would be the logical Hilbert space, and the physical Hilbert space is the one that V maps to. So here I'm defining the code for you by telling you what V is. So it maps you from the Hilbert space of one qubit to the Hilbert space of 3 qubits, which we'll call A, B, and C. And the way that this V acts is defined on this page. So let's just say we have an arbitrary state psi of Q. So by an arbitrary state, I mean, so we have I running from 0 to 2. Those are the three basis states of Q. These CIs are arbitrary coefficients, and this is just an arbitrary vector in the Hilbert space HQ. And V will map this to what we'll call H tilde, which is a state in ABC. And it's just this. So it maps, as you can see, it doesn't change the coefficients. It just maps the i's to the I tildes. And the I tildes are defined here. So 0 tilde is this state in the Hilbert space HA, HB, HC. And 1 tilde is the state below that, and then 2 tilde is the state below that. And so this is, maybe, if this is your first time seeing it, it's a lot to unpack. Like, why is it defined exactly this way? And you'll see, actually, why it's so nice. But one thing that you should take away from looking at this is that each of these states is entangled between A, B, and C. And it's invariant under cyclic permutations of A and B and C. So you could take 0 tilde or 1 tilde or 2 tilde, permute A, B, and C, and you would see that you get the same state back. Okay. And in fact, so ignore this for the moment. We'll come to this momentarily. But you can suggestively draw this code as follows. You could say, I'm just drawing the circle. This is just a picture that I'm free to draw. And so each dot is one of the qubits. And if I want, I can draw it this way. And so now you can more directly see the analogy to ADS-CFT, where Q here is thought of as living in the bulk. It's like the ADS degree of freedom. And then A, B, and C are all parts of the CFT. And what we're going to see is that no one knows anything about Q, but any 2 has all the information about the state of Q. And to prove that, notice that you can define this unitary. So this is a unitary acting on AB. And it's defined here. This is what it does. It takes like 0, 0 to 0, 0, takes 0, 1 to 1, 1, and so on. And it's an exercise that I'm going to leave for you to convince yourself that this unitary does the following thing. If you took some arbitrary state psi tilde on ABC, so remember the tilde is just my notation here for, like, if you took psi and acted V on it, you get psi tilde, where the coefficients are the same, but now the basis states are tilted. So if you took psi tilde on ABC, and then you acted UAB on it, so this is a unitary that acts non-trivially only on A and B. It's tensored with the identity on C. And remarkably, so what it does, you can convince yourself from the definition above, is it pulls out psi and puts it on A. And then, so it makes the state like this, where chi here is just some entangled state that is independent of psi. It doesn't matter what state was encoded in A, B, and C. But for definiteness, I can tell you it's just it's just this state, this like maximally entangled state between the quadrats. And okay, so this is true. You might say, fine, not a big deal. What's important is that from the cyclic symmetry, you can convince yourself that there also exists a UB. So you can convince yourself there exists a UBC and also a UAC that does an analogous thing. So it's also true that there exists a UBC such that it sort of pulls out psi and puts it on, say, B. And then UAC, you could say, pulls out psi and puts it on C. And you know enough, we have enough written down on the page for you to actually prove this to yourself. And this is called the quantum error correcting code for the following reason. Because even if you lost A or B or C, you could still recover the state psi, which is the state of the logical qubit. So for example, this is very useful to quantum information theorists because, for example, if I wanted to send you a qubit or a qtrit Q in the mail, I could just send it to you, but then the mail's not perfect, so there's some probability P that it gets lost in the mail. And if it gets lost, then we just lost that state forever, and I'll never be able to tell you what it was now. Okay. And we could maybe do a little better, have a little safer of a procedure, if instead I first acted V on Q, so I embedded it into a state on ABC, and then I put A into a little envelope that said A, I put B into a little envelope that said B, and I put C into a little envelope that said C, and then I mailed each of those individually to you. And now, if you get them all, of course, you're going to know exactly how to figure out what the original state of Q was. But even if any one of them is lost, like if B doesn't show up in the mail, you just get the envelope labeled A and the envelope labeled C, you're still going to be able to figure out what the state of Q was, because you can just take UAC, which you know, act that on A and C, and then you have the information of Q. So it's just really cool because in quantum mechanics, there's this no cloning theorem. Right? We couldn't have cloned the information and sent it to you redundantly that way. But we can sort of spread the information out non-locally among these different parties, such that the information is, in some sense, in the correlation between the systems rather than in any particular local system. And so that's what a quantum error correcting code is. This is one example. And one lesson from Theorem 1 is that ADS, the ADS physics, is encoded into the CFT in a way analogous to this, like a quantum error correcting code. And on some level that's independently interesting, but on another level, that, for example, opens us up to a lot of technical insights, because now we can use the tools that have been developed for the last 20 years by quantum information theorists to actually learn more things about ADS CFT. So that's, for example, how people realized that we could use the PETS map to reconstruct operators. The PETS map was known in quantum information theory. It was known that it helped you reconstruct things in quantum error correcting codes. But really no one thought about using it because we didn't think about ADS-CFT as a quantum error correcting code before results like this. Okay. So I'll mostly leave it as an exercise for you to confirm, for example, that if you took the 3-Keytrick code, that it satisfies each of the conditions of theorem 1. So for example, right, so in theorem 1, the first condition was like, if you told us, like if you took AB, let me say it this way, that it told us that like there should exist, or for any operator on Q, so for any phi Q, there should exist some operator on AB such that OAB V psi Q equals V phi Q psi. So this was condition 1, and in fact it's true. And the operator is just it's like UAB. You first act this UAB that we defined above, which pulls out psi and puts it on A, and then you kind of like act phi on A. So you take the same phi, act that on A, and then you re-encode it into AB. So the OAB that does this, that satisfies this equation, is this one. So you can prove that to yourself in more detail if you like, and you can also show that this is all true for some operator on BC and AC. Okay, so that's condition 1. Condition 1 is satisfied, and by theorem 1, therefore, condition 2 must also be satisfied. So it must be the case that there exists some operator A acting on AB such that for all rho, these density matrices rho on HQ, the following thing is true. And I will leave that as an exercise for you, or you can come talk to me afterwards and we can go through it. But this will be, I think this is an illuminating way to understand the significance of theorem 1, because like here we've figured out that condition 1 is true, so you know condition 2 must be true. So you can go ahead and try and see it, and yeah. On the last line of up here. Yes, phi A in the sense that it's the same operator, but now acting on A. Yeah, my notation's a little weird, but because if you act UAB, it sort of pulls out psi on system A. Is that clear? Okay, yeah. Okay. Good. So, yeah. Yeah, good. That's a good question. So, in the 3-Keytrick code, the area operator is something. It's going to be a number. I think the operator is log 3 times the identity on AB. So it's kind of a simple operator, and it's like the interpretation is it's the entanglement in this chi here. So it's in some sense, if you have AB, like these two physical qubits, there's two contributions to the entropy of AB. Like they're two qubits that have some, they're in some quantum state, and so they have some entropy. And part of that entropy is the entropy in Q, because they know the state of Q, so their entropy has to include the entropy of Q. But there's another contribution, which is the entropy associated to their entanglement with C. And that is the area piece. Yeah. That's an excellent question, and one that I wish I could dwell on longer, but I want to talk about some other aspects of this, but I'd be happy to talk about it more. Okay, so yes. Yeah, here, I guess what I've written is like in a general language, but I'm meant to be discussing the toy model, the 3-Qtrit code. And so here, what I wanted to write was, you can confirm that if you took the 3-Qtrit code and the V that we defined the 3-Qtrit code with, that it in fact does satisfy this condition too. Yes. Yes. Yeah, good. So here, calling it A hat, suggestively like the area, is, yeah, it's a little loose. It's because, you know, as you're saying, there's no real geometry in the system. It's just some Qtrits, so it's not really an area. I'm calling it A hat more as an analogy to ADS-CFT, where we believe that the operator that plays this role is the operator that in ADS-CFT shows up like the area operator. Okay, good. Yeah. Yeah, up here. Yes. So I could be. Sorry. Yeah. Yes. Yes. All of these could be mixed. Everything still works. Yeah. Yeah. Okay. Uh-huh. Yes. So, oh, sorry. I wrote B, sorry, and I meant SQ. Yeah, I meant SQ. So it's the entropy of the logical Qtrit. And so one reason why you should expect this formula to be true is that if I gave you Qtrits A and B, you could use them to figure out the state of the logical Qtrit Q. So the entropy of AB must be at least the entropy of Q in that case. Okay. So what we've established here is that in these fixed QES code subspaces, CFT subregions can reconstruct operators in their entanglement wedge. And we saw some explicit schemes for doing it, like the PETS map. But I claim to you that we're not done, because there's more to life than fixed quantum extremal surface subspaces. Because say we want to do, we want to realize our initial goal. We want to reconstruct some operator in a black hole. So let's say we have, so this is a time slice of ADS, like we've been drawing. Here, this circle in the inside is like a black hole horizon on this time slice. So this is a black hole. And we have some operator phi that's acting inside. And we want to ask, can we reconstruct this phi in the CFT? And to ask that question, let's consider a warm-up question, which is, can a subregion of the CFT do it? You're going to see that's actually, it's going to be important that we start from this warm-up question. So let's say, instead of trying to reconstruct phi on the entire CFT, we're just going to ask if we can reconstruct it on this subregion down here, B. And this is going to actually be a more general case, because if you want to, at the end, you can say, well, what if I take B to be everything? And then we can ask, can B reconstruct it? So this is sort of the right way to approach the question. So theorem 1 said that we, yes, can reconstruct a version of phi that works in a fixed QES subspace if and only if this black hole is in the entanglement wedge of B for every state in the subspace. So we need, okay, so we're looking, like, there's going to be some Hilbert space associated to this black hole that we're going to say is, this is of dimension e to the a over 4g, where a is the horizon area of the black hole. This is sometimes referred to as the central dogma. I'm just using for now, the usual idea that as an outside observer, you can describe a black hole sufficiently as a quantum system with a Hilbert space of this dimension. And the Hilbert space of this black hole, we're going to regard this, let's just say that there's no excitations outside for now. So we're going to consider some subspace of ADS that we're going to call H black hole that's of this dimension. And we're going to ask if it's indeed the case in this situation that the black hole is in the entanglement wedge for all states. And we'll see that it won't be. So consider the, say, maximally mixed state. So rho mm just means maximally mixed. That is, so this is the maximally mixed state in this subspace of the ADS Hilbert space. And it's just this, even mixture of all of the black hole states. If you like, we could take a thermal state, and it would be approximately one of these maximally mixed states. And the entropy of this black hole in this maximally mixed state is A over 4G. Like you compute this by plugging rho mm into the formula for von Neumann entropy. Okay. So if you actually write down the black hole metric here, you can find, and B is some subregion of the boundary. You find that there are these two particular extremal surface candidates. There's this one up here, which we'll call gamma 1. So this one, gamma 1 is, homologous to B. It's anchored to the boundary of B, and it runs through the ADS and includes the black hole. So the black hole here is in the entanglement wedge if gamma 1 is the minimal extremal surface. But there's another one, another candidate extremal surface, gamma 2. Gamma 2 runs down here, and it's, let me erase these. And so it's also extremal in the sense that it's, it extremizes area over 4G plus the bulk entropy under local perturbations of the surface. So they're both extremal in that sense. And so the QES prescription told us that the entropy of capital B is computed by taking the minimal one. Right? So we have to ask which of gamma 1 and gamma 2 minimizes the area plus entropy. Yeah. Yes. Yes, you could consider this one. I am going to, let's say we neglect that one for now by dialing the size of B such that that's going to have more area than either one. But you could do that. That's generally more appropriate if this black hole has like some connected wormhole geometry to something else, so that this surface that wraps the horizon is really like the minimal part of the throat. But yeah. Otherwise, it wouldn't be extremal. Yeah. Okay, good. So the statement is that, can I copy this? Oops, I don't know what copy is. It's okay. Oh, it's the second from the left. This one? Let me try. Oh, well. Let me just draw it again. So. Okay, so there was this black hole, and in this setup, there was these two extremal surfaces. There could be others, but we're going to you can consider setups where there's just these two that we have to worry about. And in this case, the black hole is in the entanglement wedge of B for some state, if and only if the area of gamma 1 over 4G plus the entropy of the black hole and that state is less than the area of gamma 2. Sorry, I wanted to. Over 4G. Right, so we're just asking which of these extremal surfaces is more minimal, like what minimizes the area plus entropy. And so we're just saying that's gamma 1 if the area plus entropy of gamma 1 is less than the area plus entropy of gamma 2. We're neglecting the entropy of matter fields because we're just not exciting anything, so it's going to be negligible. And you can explicitly do this computation, of the area in each case as a function of how big B is in, say, the BTZ metric. And you can also say if the black hole is in a pure state, so like its state is something like psi, then its entropy is 0. And in that case, so I'm trying to say, in that case, the black hole is in fact in the entanglement wedge of B. You can say B is of a sufficient size, like 3/4 of the boundary. If B is 3/4 of the circle, then it will be the case that the area of gamma 1 will be less than the area of gamma 2. And if S of BH is 0, if you just consider some state like that, then the black hole is in the entanglement wedge. Okay, no big deal there. But it'll simultaneously be the case that if the black hole is in this maximally mixed state, then remember, right? So its entropy is this, A over 4G. And you can easily make it the case such that, what do I want to say? That the black hole is not in the entanglement wedge of B because it's too mixed. Because gamma 2 is minimal. I hope that's clear. I kind of went a little fast there. But so like this is the case, for example, if B is 3/4 of the boundary, the black hole is like some ADS-sized black hole, and you put the black hole in the maximally mixed state, then gamma 2 will be minimal, whereas if it's pure, gamma 1 is minimal. Okay. So the upshot here is that the quantum extremal surface depends on the state. So when the black hole is in state psi, gamma 1 is minimal. But then when the black hole is in some maximally mixed state, boom, gamma 2 is minimal. All right. So the point is that if you wanted to consider some ADS setup in which the black hole could take any state in its naturally sized Hilbert space, then the quantum extremal surface for general subregions of the boundary is not fixed in that subspace. It could be one thing in one state and a different thing in a different state. So the QES is not fixed in subspaces that include general black hole physics. So general black hole states. So, okay. And that's significant because then theorem 1 promises us nothing about operators on B working in this subspace. So So if you just tried to use theorem 1 to ask, can I ask a question about the interior of this black hole, it would just say, I give you nothing, no promises about whether or not you can reconstruct an operator inside the black hole, which is a shame and motivates us to ask if there's any way we can do better using the quantum extremal surface formula to learn what we can reconstruct in these more general non-fixed QES subspaces. And the answer is yes, we can. So now we turn to the topic of reconstruction in larger code subspaces. So when we want to consider more general setups, like bulk states that have black holes and so on, this next reconstruction theorem will be the one that nicely applies there. So this is going to be theorem 2. And it's a generalization of theorem 1 that was found in 2021 by me and Jeff Pennington. And it says the following. So really, all that's different is we have the exact same setup as theorem 1, but instead of assuming that the QES is the same for all states in H code, we won't assume that. And we're going to get something that looks, and then the output is going to be something that looks kind of like the output of theorem 1, but is appropriately weaker, because we have a weaker set of assumptions. Okay, so we're going to let H equal HB tensor HB bar as before. And remember, this is morally like HCFT. So HB and B bar are some division of the CFT. And again, we have H code, which we're going to divide into H little b and H little b bar. And you'll see what defines little b. So unlike theorem 1, where little b was something fixed for all states, little b here will be something that is going to minimize the generalized entropy, and you'll see that. So H code here is supposed to be like an arbitrary subspace of HADS. So this is a subspace that can be very big. It can include black holes. It doesn't have to have a fixed QES. Okay, and now here, as you'll see, it's going to be important that we generalize, we allow more structure. It's not important that we have more structure in these Hilbert spaces, but we're going to allow it and get more out of allowing that structure. So this H little b, for example, is allowed to have some structure like H little b factorizes into H little b 1, tensor H little b 2, and so on, all the way to, say, H little b n. And then B bar, H B bar can be the same. So the point here is that, yes, in the bulk, you have little b and little b bar, but it can matter. So here I'm going to draw a picture where we have capital B and capital B bar. Those are the CFT subregions. And if you like, so little b is still, say, morally like the entanglement wedge of capital B, and little b bar is morally like the entanglement wedge of B bar. But now, just like in ADS CFT, little b has a little bit more structure. You know, there's some locality. There's some bulk points. And so I'm drawing little dots in little b those are more like how, B1 might be this degree of freedom here, and then B2 might be this degree of freedom here, B3 might be this degree of freedom over here, and so on. And B bar has the same decomposition, if you like. So little b bar 1 might be that degree of freedom, little b bar 2 might be this one. Okay, so this is the picture you might have in mind when seeing the setup of this. Okay, so we have these Hilbert spaces that you think of morally analogous to ADS-CFT like this, and we're going to let them be finite dimensional Hilbert spaces, just like before. And actually what we're going to do here is we're going to say, so in the setup of the theorem, we're going to have a state. So this state didn't appear in the setup of theorem 1. So this is a difference, and you'll see why we have to do this. It's nice, it's important. So let psi, which is a state on little b and little b bar, and capital R, which is some arbitrary reference system I'm introducing, be a state in H code tensor with this reference system. So this reference system is just there for generality. It's just like saying, imagine you have some reference system over there, and it could be possibly entangled with your bulk. Okay, so you could have some ADS state entangled with something else if you want. Okay. And finally, let me give you a definition. We're gonna talk about product unitaries. So H little b prod, for example. Prod is short for product. So let me just write product this first time. Oops. And by whenever I write something like U little b product, what I mean is it's a unitary acting on little b, but it factorizes according to this product structure that we were allowed to assume was special for little b. So it's something like U sub b sub 1 tensored with some unitary acting on b2. It can be a different unitary, so let me put a prime just to make it clear that it doesn't have to be the same one as this one. And then tensored with unitaries acting on all the other points in B. So this is just a general product unitary that we've written here. And at this point, you might be getting a little worried. Like, this seems like we're introducing a lot of new stuff that didn't appear, say, in Theorem 1. And you'll see the role of this. I'm going to try and explain that as we go. But the statement of the theorem, to show you that first, is that given everything we've said, then the following are equivalent. And again, it's going to be two conditions. The first one, a reconstruction condition. The second one, the quantum extremal surface condition. So this one says, for all product unitaries on little b, there exists some unitary on capital B such that the following equation holds. So here, I've just written something that's very similar to the condition 1 of theorem 1. But now, instead of saying that if you took any psi and acted any operator on little b, and then acted v on it, that there was an operator on capital B that did the same, it's saying we're only promised that for product unitaries on little b. And it has to be a unitary on capital B that reconstructs it. And likewise for B bar, the B bar system. And for technical reasons that are important, but I won't dwell on right now, that won't be important for your general understanding. You should include this reference system R we introduced with capital B bar and the complementary statement. So you're just taking the complementary region to B in the state. Good. You could imagine it as analogous to just a point or a small subregion, like some smeared out point. Technically, at the level of this theorem, these are all finite dimensional Hilbert spaces, and so you might just imagine them as like qubits that are analogous to points in the bulk. But yes, the analogy is that each of the little b's are kind of like little points in the bulk. Yes. Good. Yes. V acts on. Yeah, I didn't write this here. Yeah. V maps from H code to H, so it simultaneously acts on all of H little b and little b bar. Yes. Okay, and then so that's condition 1. And it looks a little bit like condition 1 of theorem 1. But it's different, as we said, because the operators you're promised to be able to reconstruct are these product unitaries, not general operators. Yeah. Good. It does not. So this U doesn't necessarily have any particular structure. It's just a unitary on capital B. And we're going to see this is actually maybe more useful than you might think that we're going to conclude after writing this theorem that all we can do with the CFT is reconstruct product unitaries in the bulk. And that's not going to be the case. What's going to be the case is that this is just what's promised you. Yeah, this is what's promised to you in the given that you just know some subregion is the entanglement wedge for one state. But generally, you know more than that. And so generally, you can reconstruct something, more general operators. We'll get there. But yeah, these product unitaries won't be the only thing you can reconstruct, but they are the thing that shows up in this condition of this theorem. Okay, so condition 1 is this statement. And yes. Good. For now, I'm not taking too seriously the division of the bulk into different subregions. If you wanted to do that, then probably it would be most convenient to, say, fix a gauge and then decide on subregions there, or do something more complicated like some gauge invariant definition of your operators. For now, what I would like is that you to take these little b's as roughly analogous to bulk subregions, and then later we can talk about how to more seriously apply this theorem to ADS-CFT. Yeah, maybe that. I'm not sure. Let's see. So yeah, let me leave it at that for now. So we're not going to have diffeomorphisms in this Hilbert space. For now, they're just finite dimensional like qubits. Yeah. So the second condition that this condition 1 is equivalent to is the statement that, so it essentially says that if you were to compute the von Neumann entropy of capital B in the state psi, remember if I scroll up, psi was this state that we started with, and the state that appeared here in the reconstruction. and we map it to a boundary state with V, then that entropy equals the area of little b. And I'm actually going to write it this way. So it's like A sub capital B of little b. So this is just like the area term before, but so it's in the sense that it's essentially some operator that is independent of the state. So it's some operator that depends only on V. And I'm going to define it for you shortly. But it's morally like the area. And the von Neumann entropy of this region little b in psi. And it's not quite just this bare bones thing that I've written so far. It's a slightly stronger statement that for all product unitaries, this has to be true. So it's not just true for psi that we were given, but also true for any state related to psi by acting a product unitary on it. In other words, any state that has the same entanglement structure as psi. Okay. And again, likewise, this has to hold for the barred regions. Okay, so finally, there's actually a third condition. So theorem 1 was just the equivalence between these two things, but one of the downsides of theorem 1 was that there was no extremality, right? We said it was kind of like explaining the quantum extremal surface formula and what it means for reconstruction, but it didn't anywhere in it include some statement like you had to find the minimal extremal surface. In fact, in this theorem, we're going to have something that's closer to that, or it's going to have the minimality. So the statement is that both of these conditions imply a third condition. That for any B prime, which is, I'll write it this way, some subset of little b bar. So it's like little b and little b bar had this special tensor product structure, and B prime is just some combination of those tensor products. So a picture will make that much clearer. So again, remember we had B and B bar, and they divide it, and then their entanglement wedges were, say, little b and little b bar. Little b prime is just some arbitrary other region that's, say, homologous to capital B. So say something like this. So B prime is, say, everything here. So it could be some combination of parts of little b bar and parts of little b. So the statement is that for any B prime like that, the area of B prime plus the entropy of B prime in the bulk state is greater or equal to than the area of B plus the entropy of B. So in this sense, this little b here, the one that shows up here, and the one that you can reconstruct, that little b, minimizes this area plus entropy. Okay, and so on the one hand, that's nice because it says the bulk region that we would call the entanglement wedge, the one for which this equation is true, say. So the entanglement wedge of capital B minimizes the generalized entropy. So that's pretty good. That's kind of like the extremal, like finding the minimal quantum extremal surface. But it is a little weird that it's, you might think it's kind of strange that it's just a minimization. Where's the extremality, like the extremality in the time direction? Say, is this inconsistent with that? And the short answer is, this is pretty good in the sense that it's analogous to the prescription, the quantum extremal surface prescription, if you were, say, applying it at some moment of time reflection symmetry. In that case, finding the minimal QES is just equivalent to finding the surface in this given time slice that minimizes the generalized entropy. So you could say what we've done is derived that special case. On the other hand, it's a little mysterious how, we're not actually assuming time reflection symmetry anywhere here. So it's kind of like saying this code perspective seems to apply to that case and is not so clearly related to the time direction in gravity. So I don't want to confuse you by delving into this point, but I think this is an interesting active area of research, how to get a theorem like this, some theorem 3, that gets the full quantum extremality. Say so it's minimal in the spatial direction like this, but also maximal under deformations in the time direction. So that's an open question that I'm very interested in. I'll say more about that later, at the end of the next lecture. So, okay, so we have this theorem with these 3 conditions. So 1 and 2 are equivalent, and they imply this third one. I haven't fully explained all the pieces to you yet, because I haven't, for example, told you what this say, A of little b is. I said it's kind of like the area. In fact, so it's very related to the A that showed up in theorem 1. So whenever you assume the stronger thing, like you assume that you're just applying theorem 2 to a fixed QES subspace, this A reduces to the A in that theorem, but it's actually more general. And it was important that sort of a more general A showed up in this theorem when we proved it, because we, in this theorem, are not requiring that all quantum extremal surfaces are the same for all states. So we need to talk about the area of many different surfaces. There's more than one surface in the game now. And so we had to define some area for all relevant surfaces. This A does that, and I'll define that for you momentarily. But remember, the takeaway of this theorem is that this is sort of supposed to be the general reconstruction meaning of the quantum extremal surface formula, not just in the fixed QES special case, with the caveat that the extremality part is still a little mysterious, but it has this minimality. We understand that part. Okay, so let me turn to trying to finish explaining the pieces to you, in particular this A, B, B. So first off, what's with this subscript capital B that I'm putting here? We didn't have that before. And on the one, okay, so basically it's allowed that it has some dependence on capital B, because the only place in this theorem that it showed up really, the main place it showed up was in this equation in condition 2. And there's a capital B on the left-hand side, so there can be a capital B on the right-hand side. It also showed up in condition 3, but again, it shows up on both sides, so that's allowed. So it's not like we're doing something illegal by adding in some dependence on capital B that it can't have. But why should it be there? So roughly speaking, the ADS-CFT version of this is that this is defining the area of the surface bounding subregion little b that is homologous to this boundary region capital B. So this is just a detail that maybe you wouldn't have been concerned by if I didn't bring it up, but let's say you had capital B, and what we're going to allow in this area function, right? This is a function that sort of takes in some subregion of the bulk, little b, and then outputs a number. And it's gonna make sense for any subregion of the bulk. So even ones like this that are, say, isolated away from capital B. And if you asked this function what the area of this guy was, it would actually output. It only outputs areas that are homologous to capital B. So it wouldn't output the area of this surface per se. It would output the area of that plus some surface that you should imagine as hugging the boundary with infinite area, just to make the subregion homologous. So it's like the surface that only includes the bulk points on little b, no other bulk points, but is homologous to capital B. Anyways, so that's what the subscript capital B is doing. So let me finish defining the area for you. So the idea is that yeah, what do I want to say here? Let's just say, okay, so we have this V, and in general, so this V mapped from like h little b tensor h little b bar to the capital B's. But let's just say, in general, you have a V that maps from h little a's to the capital B's. Okay, and then you want to pick some bulk region that we'll call little b, and it'll be just some collection of these little a's. So it might be like h. So this is h. Sorry, this is a sub I1, and then a sub I sub 2, and so on. So maybe it's so the picture we might have is like B is this boundary subregion. All the A's are these different dots in the bulk, these different bulk points. And maybe B is like, maybe B is this subregion bounded here. And it's like the union of A5 and A4 and A17 and so on. So in this case, yeah, in this case, B would equal like A4, A5, A17. And we just want to weigh, yes. Yeah, you're saying, what is the principle that determines small b here? So actually, I've sort of done a switch in language. So on this page, when I'm talking about small b, I'm talking about an arbitrary bulk region. In the theorem up here, you are kind of supposed to imagine that little b is the entanglement wedge. It's not just any bulk region, it's specifically the entanglement wedge. So in the theorem, the little b that, say, satisfies this boxed equation is the one that also satisfies condition 3 and is minimal in the sense of this bottom boxed equation. And now on this page, I'm just talking about an arbitrary bulk region, and so I just picked, for example, this one that was isolated from the boundary. Yeah, now that I'm trying to define for you what this function a of little b is, there's no correspondence. Yeah, yes. Yes. Okay, so yeah, so what we would like is, given some general v and given some general little b, to have some way of ascribing some area to that. So we're going to call it area because in ADS-CFT it's going to be analogous. It's going to show up as the area of the quantum extremal surface. So to any V, there's a special state. We're going to call it the CJ state. And it's defined as follows. You take, so remember V mapped all of these little a's to the b's. So you take a state that is maximally entangled between, say, A1 and some auxiliary system R1, and then also A2 and some auxiliary system R2, and so on, to AN entangled with RN. And then you act V on it. And this gives you a state that you call the CJ state, which is a state on capital B, capital B bar, and then all the little r's. And you might think of this graphically as we started with a state that was, say, entangled between A1, like this was A1, A2, AN, R1, R2, Rn. So these angled lines are supposed to be like maximally entangled states between each of these. And then you input all of these into V, and then V outputs a state on BB bar. And these you just keep around. And the state on all of these legs is called the CJ state. So I don't know if this circuit diagram makes sense to everyone, but it might help. So yeah, all of these, this is just like a tensor product of a bunch of maximally entangled states. Okay, and then given this CJ state, I can now define for you this A. And it's just if you let B be, again, we said this before, we're just imagining that B is just some collection of the input factors. And then let's let little r be defined by the associated entangled factors. So remember R1 is entangled with A1 and so on. So Ri1 is entangled with AI1. Then this A of little b is just defined as the von Neumann entropy of capital B little r in that CJ state. Okay, so all of this was just to tell you this equation. So you just define the area this way. It's something that depends on V, because V shows up here. And it depends on the subregion of the bulk you're talking about, because that shows up here. Right, so B tells you what R is. So it depends on the subregion of the bulk, and it depends on V, and it gives you a number. Okay, and turns out you just define it this way, and then this theorem too is true. And you could, as an exercise, prove that given the assumptions, the stronger assumption in theorem 1 of a fixed QES subspace, that this reduces to the A there. So for example, in the 3Q trick code, you can prove that this reduces to the A that I asked you to derive in the exercise there. And now, okay, you could ask, why this A? Why? So this seems kind of weirdly complicated. We went through it kind of maybe a little fast, but it looks kind of perhaps weird. You want me to believe that this A is somehow related to the geometric area in ADS-CFT. So why, for example, should we think that when applied to ADS-CFT, this becomes like the area of the QES over 4G? And the basic reason, so yeah, why this A? And the basic reason is that this function, believe it or not, is what I'll call functionally unique. So any other area that you could define, so any other function that just took in some bulk subregion and then outputted a number, would agree with this one about all the important stuff. So it would agree about the area of the quantum extremal surface and would agree about the position of the entanglement wedge. And there's a proof of this in that paper that I had with Jeff in Appendix A. But rather than go through the proof, I would like to just show you some intuition behind why this turned out to be the correct reconstruction statement. So remember, the statement was, the statement is supposed to be that in terms of ADS CFT language, that if you have some boundary subregion capital B and you have some bulk state psi, and in this, given this bulk state, the quantum extremal surface is, say, there. So little b is the entanglement wedge of capital B. What you're guaranteed from knowing this is that for any product unitary on little b, so this is a unitary that sort of factorizes across local bulk points, you could reconstruct a unitary on capital B that does the same job when acting on the state. So you could satisfy this equation. So you could do this. But let me emphasize something that was implicit in theorem 2, but I didn't really emphasize it there. You're not guaranteed that if you had some other bulk state, let's say omega, and you acted the same bulk product unitary on this other state, and then mapped that to the boundary, that this u of b would do the same job in this case. So let me, so given the setup, this equation can be true, and then this bottom equation, or yeah, this is, the bottom box is also true. So it's, the left and right hand side are not equal. So the only difference here is that we've swapped out psi for omega. So the reconstruction that you're guaranteed is state specific. That's different from theorem 1. Theorem 1 said for any bulk operator, you can find a boundary operator that just does the same job. Works on any state in this subspace. So here, this operator is guaranteed to do the same job on the state you're talking about, the one whose entanglement wedge you were considering. So let me say it had to be this way, state specific, because whatever the quantum minimal surface formula implies, it better be about just one state, which is the state that you use the formula, the quantum extremal surface formula in, because it doesn't know anything about a choice of subspace. Right, so this is different than in theorem 1 because theorem 1 had the strong assumption that all states in H code had the same entanglement wedge. So if you knew what the entanglement wedge was for one state, you knew it for all states. Here you don't. If you know it for one state, you're not promised anything a priori about other states. Okay. So this might make even more sense when I say the following. You can ask, why are we only guaranteed that we can reconstruct product unitaries? And the reason is, again, that the quantum minimal surface formula can imply something only about reconstructing operators with respect to a particular state, and in the entanglement wedge of that one state. Any operator besides a product unitary could change the entanglement wedge, and then which entanglement wedge you were talking about, then you could ask which entanglement wedge can you reconstruct in, the one before or after acting the operator. So I'll give you an example of this. So assume for contradiction that you could reconstruct general unitary on little b. So not product. So maybe it looks like this. So B, capital B is this large region here. And let's say we're considering a bulk state that has 2 black holes. And these black holes are going to be, they're big quantum objects with big Hilbert spaces, and let's say they're entangled. Okay. And because they're entangled, the entanglement represented by these lines here, the QES, the minimal QES, let's say is this one, that includes both of them in the entanglement wedge. So you can actually find a situation like this. But there could be, you can find a situation in particular where there is another extremal surface that's not minimal, but it's extremal and it does this. So it would include one of the black holes and not the other one. It's not hard to construct such a situation. So the point here is in this setup, there's 2 black holes that are in the entanglement wedge of B. And these black holes are entangled. They're in the entanglement wedge because the minimal QES is here, this shaded line. But there's another one that's not minimal that's going between them. But now, here's the key point. Let's assume that you could act any unitary in the entanglement wedge of capital B, then you could in particular act a unitary in the entanglement wedge that acts on both black holes, and then they're in some pure entangled state, maps them to some factorized state. So it maps them, so again, I'm just redrawing the setup, so you have B on this side here. You have 2 black holes, but then now they're not entangled. We've just mapped, we've basically just mapped some 0, 0 plus 1, 1, but the black hole version of that with a lot of states to 0, 0 or something. So from some entangled pure state to some non-entangled pure state, you can definitely do that with a unitary. And then now by construction, we still have, the geometry hasn't changed. We have the same extremal surfaces, but now this one, which was minimal before, is not minimal any longer. This one's now minimal. It's minimal now because it doesn't have to cut through all of this entanglement. So before, if this dotted line had much more area plus entropy because it included the entropy of this black hole because it was entangled with this one. But now the entropy of both black holes is 0. So this is the minimal guy. Okay, so the point here is that if you could, say, reconstruct any unitary in your entanglement wedge, then you could do something like this, where you act a unitary on capital B, it dramatically changes the location of the QES, and that's a problem because, for example, you would have changed the entropy of the complementary region, B bar, right? So if you had computed the entropy of capital B bar, it would have said, find the minimal QES. So in this case, it's this guy, the shaded line. And on the right case, it would have been this guy, which has a different generalized entropy. So you would have changed B bar's entropy. So S of B bar before would not have equaled S of B bar after. Sorry, the handwriting's bad. That's a problem because a unitary on capital B cannot change the entropy of the complementary region. That's a claim. I don't know if that's known to everyone in the audience, but that's true. You can take the formula for von Neumann entropy and convince yourself that a unitary on the complementary region can't change the entropy. But if you could have reconstructed any unitary in your entanglement wedge, then you could have. Okay, so yeah. Yes, and so in this example, what I wanted to do was say that on the left, they're in some very entangled state with each other, that's pure, and then we act a unitary that changes them both to some pure factorized state. If that makes sense. So, so before it was like, I said it was like this, but obviously that's what it would be like if they were qubits. So really they have many more states. So like they have e to the a over 4g states in their superposition. And then we change them both to, say, this state. Or maybe better is to say that we change them both to some like energy eigenstate. So they're not entangled. Good. Why does U product avoids this problem? Because U product has to respect U product would have to act, for example, it could act only like, let's call this left black hole 1, and the right black hole 2. Sorry, this is black hole 1, and then this is black hole 2. U product would have to take a form like this. Some unitary on black hole 1, tensored some unitary on black hole 2. And so I'll write U prime to say that it doesn't have to be the same. And a unitary like this can't change the entanglement between the two black holes. So it can't have, no unitary like this could map some entangled state to a product state. So this is sort of an example of why it makes sense that what you can reconstruct are product unitaries, not general unitaries. And I'll leave it there for now. And next lecture, what we'll talk about is, okay, so we can reconstruct product unitaries. Is that bad? Or, is it, what if I want to do something more complicated than that? Can I do that? And then the answer will be yes, and there's some very nice things we can say about what you can reconstruct. So I think my time is up, is that right? Okay. Thank you.
Okay, thank you. More questions?
Does this kind of argument depend on how many boundaries your spacetime has?
Oh, sorry, can you say that again?
Do these kind of arguments depend on how many boundaries your spacetime has? My confusion is this: like usually you think of black hole as already entangled with a black hole which is another asymptotic boundary, right? So when you say you have black holes maximally entangled in the same spacetime and so on.
Good. Yeah. So this argument would work for any number of asymptotic boundaries. And you're right. Maybe the most familiar setup would actually be to have two asymptotic boundaries. You could consider a case where you just have one asymptotic boundary and two maximally entangled black holes that are connected by a wormhole. That is also a solution.
I have a really naive question whether these two black holes can be stationary, they attract each other. So the question is whether this kind of calculation, QES, can be also applied to this non-equilibrium. It must be. So.
Yeah, that's a great question. Yeah, so if we had these two black holes, I believe you can set it up so that this is the moment of time symmetry, and so you could, when applying the QES formula here, it would in fact reduce to this quantum minimal surface formula, and that would be the context in which I would want to make this. If you didn't like that, then you could do what we were saying before, have put each black hole in two different asymptotic regions and make a similar argument there.
Yeah, so my question is regarding this U product, and is the reason why this works more because of this U product is somehow a more local unitary operator as compared to this general UB?
Yes, the locality is very important. One thing that's interesting is that, yeah, you might have wondered if theorem 2 could have been rephrased with instead of these complicated product unitaries, we just said local unitary. And in fact, it wouldn't be true. You needed to consider basically all possible products of local unitaries.
So is it somehow related to the fact that local operations do not change entanglement entropy?
Yes, that's right. Yeah. Thank you, yes. The reason why the product unitaries are the thing to consider is that product unitaries don't change the entanglement entropy between the different subregions.
Why is S of B bar different in the left and right diagram? Isn't it given by the same RT surface?
Good. So here, in the left side, so S of B bar before is given by this left RT surface, this one here. And then S of B bar after would be given by this right RT surface, the one there. Good. So in the setup that I'm considering, I didn't specify all the details explicitly, but the minimal area surface is actually this one on the right in this setup. That's the minimal area surface. So if the black holes are unentangled, that's the QES. But if the black holes are entangled, the minimal quantum extremal surface is this one on the left because it's penalized for cutting all that entanglement.
More questions? Maybe can you clarify, intuitively explain the role of this reference systems appearing in the theorem?
Yes.
And the definition of this area, like quantity.
Yes. Okay. This reference system, the R's.
That and also R is appearing in the theorem.
Good.
If they are related.
So good. So they are actually sort of unrelated, but important for. So it's the kind of thing that you start seeing when you delve a lot into these quantum information theorems, that reference systems start to be very useful and showing up and popping up all over the place. So here they're sort of popping up for two sort of complementary reasons. So one way, so this capital R here, the one that we introduce in the setup of the theorem, this one here, is basically there in some sense because we want to write an equation like this that looks nice and has pure states psi, but we want it to be possible, we want to be able to talk about states in which little b and little b bar are mixed. And so one way to do that is to include their purification, which is just some arbitrary reference system. So really it's nothing much more than that here. Okay. The little r's that show up here turn out to be important because they're important for writing down this CJ state. And the CJ state, it's a very interesting state because it, in some sense, if you know the CJ state for some V, then you know everything about that V. So there's actually some isomorphism where like all V's have there's a one-to-one correspondence between V's and their associated CJ states. And but for that to be true, you have to include these reference systems.
But these small r's are living in the same capital R that you defined before?
Sorry, say that again. They're defined in the same Hilbert space?
Same capital R space that you defined before during your theorem.
You could, you don't have to.
It doesn't have to.
Yeah. So actually, if you look at the paper and the proofs and stuff, there are points at which we have capital R's, small r's, capital R bars, and small r bars. So yeah, they all have distinct roles to play.
Okay, thank you.
Yeah.
More questions? Yeah.
about the theorem that you said that the first theorem, first statement, there is a similar equation holds for B bar and capital B bar and R.
Yes.
And but second one holds for B bar and capital B bar. So
Oh, sorry. Yeah, this
Yeah.
should have been R.
I see.
Thank you. Yeah.
Thank you.
I can tell y'all are paying attention.
How large can the code subspace be made? You said it's arbitrary subspace of ADS.
So yeah, here the code subspace can be actually very large. So it actually turns out, I didn't emphasize this, but here H code can be larger than H. This is very counterintuitive, and certainly was not the case for theorem 1. But yeah, I hope to say more about that next lecture. But yeah, it's actually very interesting and important for ADS-CFT that H code can be larger than H, because that's actually a situation that arises physically with old black holes. And so notice, yeah, so for us understanding that, it was actually important to write this theorem and then notice that all of the proofs still worked even if H code was very big.
Another question is, when you say state-specific reconstruction, could it be that an operator can be reconstructed on the boundary for a specific state but cannot be reconstructed for another state?
Yes, and that matches your intuition with an ADS-CFT where like some operator might be acting at a bulk point that for one state is in the entanglement wedge and for another state is not in the entanglement wedge.
More questions?
Is there a toy model where this isometry has been constructed?
Good, yes. So, yes, there are actually many. And my favorite one, let's see, I have a lot of favorites. A very good one is these random tensor network models by, I think the paper was written in 2015 by a group at Stanford that included Patrick Hayden and Michael Walter, Xiaoleng Shi, and others. And that's a very good one and it's a good example of this because different states can have different quantum minimal surfaces. So.
Okay.
In the first statement of your theorem, you had written that similarly we can construct for small b bar and capital B bar R, but this reference system was tensor product for the with H code. So shouldn't that capital R should come with small b bar?
That's a great question. So yeah, good. So yeah, it looks like here that it's on the same footing as H code, but then here it's somehow on the same footing as the capital B's. And so you're right to pick up on that, but I do mean what I wrote here, where it's living, so it should be associated here with B bar. And the reason is that V here acts only on H code. So if you want, it, you know, you have some state, so it like leaves HR on both sides. So HR is on both sides, so it does show up on even on the right side, and in this theorem should properly be associated to B bar.
More questions? Okay, if not, let's thank Chris again.
Yeah. You can consider entangled states, but the product unitaries will not be able to change that.
Okay, so tonight banquet will be 6 p.m. and I put the map in also homepage so you can look at the locations. Okay, see you guys there.
So that's exactly what I hope to discuss first next lecture, and the point will be that that, yeah, so if you want to consider what operators you can reconstruct on, say, some boundary region, you should, you need to, you can start from this theorem and you can say, okay, given that this bulk point is in the entanglement wedge for this state, I know that I can reconstruct the product unitaries in this state. But I actually also know